Hello there, and welcome to Just About Earth, where the planet's longer stories are allowed to unfold at a gentler pace, and where curious things from deep time can keep us company for a little while as the day softens around the edges. Tonight, we're settling in with a subject that sounds, at first, a bit impossible. It sounds like one of those strange sentences that ought to belong to a museum placard, or a documentary narrator with a very serious voice, or perhaps a paleontologist who has spent too long staring fondly at skulls. Before dinosaurs, something almost became us. Now, that phrasing is doing a great deal of work, so let's not hurry past it. Before the first dinosaur ever put a three-toed foot on the ground, before the great long-necked giants, before the terrifying jaws and club-tails and feathered hunters, there were already creatures alive that were moving bit by bit in a direction that matters very deeply to us. Not because they were human, which they absolutely were not. Not because they looked like us, which would be a very generous interpretation of several rather lumpy fossil skulls. But because they belonged to a lineage that had started solving life in a way that would, after a very long and rather difficult journey, eventually lead to mammals. And because we are mammals, that makes them family in the oldest and least glamorous sense imaginable. If you like, take a moment and think about where you're listening from tonight. What time is it in your corner of the world? Is it properly late, with the windows dark and the day already folded away? Or is it one of those in-between hours where the mind is tired but not yet willing to admit it? Perhaps you're under a blanket. Perhaps you're doing the dishes. Perhaps you're pretending you'll only listen for 10 minutes, and then somehow waking up much later with your phone still glowing gently nearby. And wherever you are, whether it's raining, windy, too warm, too cold, or suspiciously quiet, I'm very glad you're here. And if this sort of slow wandering through Earth's stranger histories is something you enjoy, something that helps you settle a little, or simply gives your thoughts something more interesting to do than replay tomorrow's errands, then do consider liking the video and subscribing. It helps this little corner reach other people who may also want a calmer sort of science, one with fewer exploding graphics and rather more ancient bones taking their time. So let's ease into it, because this story really does begin in a place most of us don't instinctively look. When people think about the origin of mammals, they often imagine a scene set after the dinosaurs. Dinosaurs vanish, the world opens up, small furry creatures finally get their chance, and eventually, after enough evolutionary tinkering, out comes everything from shrews to whales to bats to us. And that version of the story is not exactly wrong. It's simply incomplete in a way that matters, because by the time the dinosaurs were already dominating the land, the crucial groundwork for mammal life had been laid much, much earlier. The deeper roots of our story were not hammered out in the aftermath of dinosaur extinction. They were assembled before dinosaurs rose at all, in a harsher, older world, among creatures most people have never heard of, unless they had an especially committed dinosaur phase that wandered off in an unusual direction. To find them, we have to go back beyond the age of dinosaurs and into the Permian period, a span of time so distant that even saying its name can make the modern world feel briefly insubstantial. We're talking about a world more than 250 million years ago, and in many cases significantly earlier than that. A world arranged differently, breathing differently, populated by forms of life that would not look right to us even when they are familiar in outline. Not yet dinosaurs, not yet mammals, and certainly not anything like human beings in any recognisable sense. But somewhere in that strange and ancient landscape, natural selection had already begun shaping a body plan, a feeding strategy, a way of breathing, chewing, sensing, and surviving that would become profoundly important later. This is one of the quiet tricks of evolution. It rarely builds toward a goal in the way we like stories to do. There is no grand announcement, no little sign reading future human traits under construction. There is only the practical business of survival, a jaw that closes a little better, teeth that do not all do exactly the same job, a skull rearranged in ways that happen to improve feeding, breathing or hearing over immense spans of time, a metabolism that edges toward a more active life, a body that becomes a bit more internally regulated, a bit more persistent, a bit less dependent on the exact favour of the surrounding environment. None of these changes happened because evolution had us in mind. They happened because in the lives of those animals, at those times, they worked. That, if anything, is what makes the story so remarkable. The path to us was not a straight road. It was not even a road. It was a series of local solutions to immediate problems, accumulated over ages so long that even the word age feels too short. And many of the most important of those solutions arrived before the famous reptiles ever took centre stage. The ancestors of mammals were, in a sense, rehearsing certain mammalian qualities in a world that had never heard of mammals and would not see true ones for a very long time. It also helps to clear away a common mental picture, which is that life before dinosaurs must have been a sort of empty preliminary stage, as though Earth was waiting backstage with half the lights off until the proper stars arrived. But the Permian was not empty. It was full, dynamic, competitive, and often brutal. Entire ecosystems flourished there. Vast dry interiors spread across the supercontinent Pangaea. Seasonal extremes could be intense. Life on land had already become established and inventive. Insects were abundant. Plants shaped landscapes in their own quiet way. Amphibians, reptiles, and early synapsids occupied different niches. Predators hunted. Herbivores cropped tough vegetation. Burrows offered shelter. Rivers shifted and vanished. Heat pressed down. Droughts came and went. It was a real world, not a prologue. And within that world, one split in the tree of life would matter enormously to us. Very early on, among the amniotes, the broad group of vertebrates that could reproduce away from water, thanks to protected eggs and related adaptations, one branch led toward the reptiles and, much later, the dinosaurs and birds. Another led toward the synapsids, the lineage that would eventually produce mammals. If that word synapsid sounds a little technical, do not worry. You're not required to say it out loud at a party, unless you want to reduce the number of invitations you receive. For now, it is enough to know that synapsids were not dinosaurs, not lizards, and not mammals either. They were their own major branch, and they were already present long before dinosaurs entered the picture. Some of the earliest and best-known members of this broader synapsid line are the animals that older books and toy bins have often treated rather unfairly. You may have seen one before without realising what it represented. A squat-bodied creature with sprawling legs, a sail on its back, and the sort of expression that suggests it is permanently disappointed by the weather. That is Dimetrodon, perhaps the most famous non-dinosaur frequently mistaken for a dinosaur by almost everyone who has ever not been cornered by a paleontologist. But Dimetrodon is not a dinosaur at all. It lived tens of millions of years before the first dinosaurs appeared, and more importantly for us, it was close to the mammal line. Not close in the sense that you would mistake it for a squirrel naturally, more in the sense that if you drew the great family tree of amniotes, it sits on our side of one of the oldest meaningful splits. That alone is enough to make the past feel a little less tidy than the usual schoolbook version. The creatures that led toward mammals were not small afterthoughts, scurrying under the feet of more impressive animals from the beginning. In the Permian, synapsids and their descendants could be major players. They were experimenters in body form and ecology. Some were predators, some were herbivores, some grew large, some developed striking skull structures, some had powerful jaws and differentiated teeth that already hinted at a future in which food would be processed more efficiently than the simpler grab-and-swallow strategy common in many earlier vertebrates. And this is where the phrase, "something almost became us," begins to feel less dramatic and more precise. What almost became us was not one species, not one heroic ancestor standing nobly against a lava-red sunset. Evolution is rarely kind enough to provide such symbolism. It was an entire lineage, a broad and changing branch of life, in which traits we now think of as distinctly mammalian were emerging piece by piece, not all at once, not in order, not with any awareness that they were assembling into something that, much later would define a successful and enduring group. Consider for a moment how mammalian a mammal actually is. We tend to think of fur, warm blood, milk, lively senses, efficient chewing, active lifestyles, and very precise hearing as if they belong together naturally, as if once one appears, the others politely line up behind it. But evolution is messier than that. Features arrive in mosaics. A creature may have one advanced trait and several that seem old-fashioned. Another may show a jaw beginning to change while the limbs remain arranged in a more sprawling posture. Another may have teeth specialised into different forms while still lacking other characteristics we would associate with later mammals. The fossil record of the Permian and Triassic gives us exactly this sort of mixed company. Not a clean transformation, but a sequence of animals in which the mammalian package is being assembled component by component. That matters because it changes how we imagine our own origins. Humans did not appear because mammals suddenly blossomed out of nowhere after the dinosaurs disappeared. Mammals themselves were the product of a far older process, one rooted in experiments that began in pre-dinosaur worlds. The foundations of how our ancestors eat, breathe, hear, regulate heat, and process the world were being laid in stages by synapsids and therapsids, long before any mammal looked remotely like a primate, and unimaginably long before anything stood upright and wondered about its place in the universe. There is something humbling in that. We are very attached to our own recentness. We divide history into comforting scales: human history, ancient history, prehistory, dinosaur time, and then a kind of vague geological fog where everything seems composed of mud, giant insects, and creatures nobody remembers correctly. But the real story does not arrange itself around our convenience. In evolutionary terms, many of the decisions that matter most to our lineage were made before dinosaurs. Not by intention, of course, by selection, by endurance, by what survived and what did not. And survival, in this story, is no small thing, because the Permian world that nurtured so much of this lineage also delivered one of the worst catastrophes life on Earth has ever faced. Long before the asteroid at the end of the Cretaceous ended the non-avian dinosaurs, another disaster struck at the end of the Permian, and it was even more devastating. Entire ecosystems collapsed. Species vanished on a scale almost beyond comprehension. The extinction was so severe that it nearly erased the very branch from which mammals would later emerge. When we say something almost became us, the almost is not theatrical, it is real. The lineage that carried these mammal-building traits forward came extraordinarily close to being cut off entirely. And yet, it was not. A small surviving branch endured, not because it was destined, not because progress is guaranteed, but because some populations somehow made it through conditions that destroyed so much else. Their descendants continued. They passed into the Triassic. They changed again. True mammals eventually appeared. They stayed small for a very long time while dinosaurs rose to prominence. They lived in the margins, in shadows and undergrowth and nighttime worlds, surviving as if the lineage had learned caution from deep time itself. Only much later, after another great extinction, would mammals expand dramatically into the forms we know. All of that means that the usual picture, mammals waiting politely backstage until the dinosaurs leave, misses the older and stranger truth. The deeper beginnings of our kind of life were forged in a much earlier age, among creatures that do not get the same attention because they are less familiar, less cinematic, and, if we are being honest, often less photogenic in reconstruction. Dinosaurs have a certain advantage there. A giant predator with a mouthful of teeth practically markets itself. A complicated sequence of jawbone transformation and metabolic upgrading in squat pre-dinosaur synapsids requires rather more patience. But patience is where the good stories are, and I think that is part of why this subject is so satisfying once you settle into it. It rearranges the hierarchy of wonder. Instead of seeing mammals as the beneficiaries of dinosaur absence, we start to see them as the heirs of a much older struggle. Their story did not begin in opportunity after the fact. It began in experimentation before the world most people imagine. Long before a mammal ever nursed its young in anything like the modern way, the anatomy that would allow later mammals to become such a flexible and successful group was already under construction in ancestral forms that lived beneath Permian skies. If you were able to walk through one of those ancient landscapes, though I would not recommend it from a practical standpoint, as the climate, local wildlife, and lack of roads would all be inconvenient, you would not see the future in any obvious way. You would see strange herbivores, predators with heavy skulls, sprawling or semi-upright bodies, unfamiliar plants, waterways, dust, heat, and the ordinary business of survival. Nothing in the scene would announce, "Behold the roots of your face, your teeth, your hearing, your warm-blooded persistence." And yet those roots were there, not as symbols, as anatomy. This perhaps is one of the more useful corrections paleontology offers to our imagination. The past is not a ladder leading neatly upward. It is a branching, pruning, collapsing, recovering process. Most branches do not lead to us. Most species leave no direct descendants. Whole experiments vanish. Success in one age may mean nothing in the next. The ancestors that matter are not the biggest, loudest, or most dramatic. Sometimes they are simply the ones whose particular suite of traits happened, under changed conditions, to remain workable. And sometimes the future belongs to the lineage that survived a disaster by a margin so narrow that if a few details had gone differently, there would be no mammals as we know them, no primates, no humans, no one to name the Permian in the first place. That is the scale of contingency we are dealing with. Human beings tend to speak about our existence as if it were somehow waiting to happen. But it was not waiting. It was permitted barely by an unbroken chain of survivals and transformations stretching back through animals that would never have recognized the outcome. We are not simply the children of mammals, we are the distant result of a pre-dinosaur story that nearly ended before it could pass its most important inheritance onward. So as we move into this journey, it helps to set the dinosaurs slightly to one side for a moment. Not because they are unimportant. They are extremely important, and no doubt somewhere a dinosaur is offended already. But because in this particular story they are not the beginning. They are in a way the middle scenery through which a much older lineage persisted. The mammalian story begins earlier, in synapsids and therapsids, in skull openings and shifting jaws, in differentiated teeth and stronger chewing, in changes to posture and breathing, and internal physiology, in the slow conversion of structures that once formed part of the jaw into the delicate hearing apparatus mammals now depend on. It begins in animals that looked, to modern eyes, like rough drafts composed by an intelligent but slightly sleep-deprived nature, and it continues through catastrophe, reduction, persistence, and eventual expansion. That is where we're headed. Back into a world before dinosaurs, where the line that would one day include us was already becoming distinct, already being shaped by pressures that had nothing to do with humanity and everything to do with making a living in a difficult world. And the farther back we go, the clearer it becomes that our story did not begin with the rise of mammals after the dinosaurs fell. By then, the really ancient part of the work had already been done, bone by bone, tooth by tooth, one survival at a time, in the deep Permian world where our lineage first learned what it might take to endure. To understand how something almost became us, it helps to spend a little time in the world where that possibility first took shape, because the Permian was not merely an older version of Earth with fewer familiar animals wandering about. It was a genuinely different planet in the practical sense, arranged differently, populated differently, and governed by conditions that would have felt severe even to creatures well adapted to them. This was a world that did not yet belong to dinosaurs, birds, or mammals in the way we know them. It belonged to stranger things, and not in the dramatic sense of everything being monstrous or oversized, but in the more interesting sense that the rules of everyday life were being worked out among forms of life that now feel oddly misplaced in our mental picture of prehistory. Most people, when they imagine life before the dinosaurs, picture something vague and swampy, as if all deep time before the Jurassic was one long, damp rehearsal with a few giant dragonflies moving through the background. But the Permian, especially the later Permian, was not a soft green prelude. It was often dry, seasonal, and extreme. By this point in Earth's history, most of the major land masses had assembled into the supercontinent Pangaea, a gigantic connected stretch of land that altered climate on a planetary scale. When land masses join together like that, their interiors can become very far removed from the moderating influence of the oceans. Coastal regions may still feel some relief, but the heart of a supercontinent can become punishingly continental, with hot summers, cold winters, and long dry intervals. That is not ideal if you are fond of mild weather, stable rainfall, and not being baked one month and chilled the next. So the world our distant lineage inhabited was not simply old, it was physically demanding. Vast regions were arid or semi-arid. Seasonal droughts likely shaped everyday survival. Rivers could be life-giving, but also unreliable. Floodplains, uplands, conifer woodlands, fern-rich areas, and scrubby stretches all played their part depending on region and climate. Plant communities were not yet the flowering landscapes we would know much later. No grasses rolled across the ground, no flowering shrubs waited to entice pollinators. The vegetation was dominated by seed ferns, conifers, ginkgophytes, horsetails, and other plant groups that gave the land a recognisably terrestrial but distinctly ancient look. If you stood there and took in the view, assuming you'd somehow solve the many immediate medical and logistical problems with such a trip, the landscape might in places look sparse rather than lush, practical rather than inviting. And moving through that world were animals that do not fit comfortably into the neat categories modern people prefer. We are used to sorting vertebrate life into birds, mammals, reptiles, amphibians, and fish, as though those bins were always obvious and well behaved. But the Permian is a very good place to lose confidence in that system. This was a time when many lineages carried combinations of traits that modern eyes find awkward. Bodies looked reptilian in some respects, but not in ancestry. Heads were massive or oddly shaped. Limbs sprawled or began to shift towards something more efficient. Teeth started to vary in form and function. Skulls opened and strengthened in patterns that mattered deeply to later evolution, though of course nobody at the time had the courtesy to label them for us. The creatures most relevant to our story were synapsids, but they were not alone. Amphibians still occupied certain ecological roles, especially around wetter environments. Early reptiles and reptile relatives were present too, experimenting with their own ways of life. The land was already an ecological contest, and no one group had everything their own way forever. Yet for large stretches of the Permian, synapsids were tremendously important on land. In many ecosystems, they were among the dominant terrestrial vertebrates, which is worth pausing over because it runs against the more familiar idea that our lineage began small and hidden. Not at all. The line leading toward mammals was for a very long time out in the open and deeply involved in the main business of terrestrial life. Some of the earlier synapsids, often grouped among the so-called pelycosaurs, were the kind of animals that make museum halls delightfully confusing for children, and, if we are honest, for a fair number of adults too. There was Dimetrodon, the famous sail-backed predator, frequently misfiled in the public imagination as a dinosaur simply because it looks old and alarming. In reality, Dimetrodon lived long before dinosaurs appeared and sits much closer to our own side of the great amniote divide. That does not mean you should picture Dimetrodon as some furry uncle once removed. It was still a very different animal, with a sprawling stance and a body plan far from anything modern mammals would recognise as homey. But it was part of the broader synapsid story, and its success reminds us that the ancestors of mammals were not an afterthought waiting nervously in the wings. The sail itself, incidentally, has inspired a good deal of debate and many very confident-looking illustrations. It may have helped with display, species recognition, thermoregulation, or some combination of the above. Paleontology is wonderfully honest in this way. We can often tell that a structure mattered very much without always being able to say, with complete certainty, exactly how it was used in life. That, I think, is only fair. Modern animals manage to be confusing enough while still inconsiderately alive in front of us. Fossils have even less obligation to make everything simple. Dimetrodon and its relatives were only part of the picture. Other synapsids occupied herbivorous roles, browsing or cropping plant material in a world where processing food efficiently could be the difference between steady survival and a very unpleasant week. That mattered because land plants are not a generous food source unless your body is designed to handle them. Plant tissues can be tough, fibrous, and nutritionally stubborn. Eating them well often requires specialized teeth, powerful jaw mechanics, gut capacity, or all three. One of the great developments within the synapsid line was precisely this growing sophistication in the skull and feeding apparatus. The old simple pattern of teeth all doing roughly the same thing began to give way to differentiation. Incisors, canines, cheek teeth, grinding surfaces, slicing edges, and stronger bite mechanics gradually became more important. This was not aesthetic improvement, it was engineering. And engineering mattered in the Permian because the world was not forgiving. A body that could feed more efficiently, process food more thoroughly, and sustain higher levels of activity had options, not infinite options, naturally. Evolution does not hand out miracle warranties, but it does reward workable design. The Permian landscape placed heavy demands on vertebrates. Temperatures could swing, water availability could shift, food resources could be patchy. Predators had to catch prey in open and difficult environments. Herbivores had to make poor quality plant material pay its way. Small animals had to avoid being eaten while also not drying out, starving, or overheating. Survival was not a broad philosophical matter. It was immediate and rather repetitive. If we had the chance to observe one of these ecosystems quietly for a day, what might strike us most is not that everything seems primitive, but that everything is already highly committed to life on land. That is an important point. By the Permian, terrestrial ecosystems had matured significantly. This was not the first awkward venture from water onto shore. Plants had long since spread across the land, so had arthropods. Vertebrates had diversified into forms capable of spending their full lives away from permanent water sources, especially through the evolution of the amniotic egg and related reproductive strategies. This freed them from the old amphibian dependence on watery breeding grounds and opened the door to a far broader conquest of inland habitats. That reproductive shift may sound technical, but it was transformative. Once vertebrates could reproduce successfully away from ponds and streams, the map of life changed. Dry interiors, seasonal environments, uplands, and harsher terrains became available in new ways, and in such places the competition to become good at land living intensified. That competition shaped posture, skin, breathing, feeding, growth, and metabolism. It is one of the reasons the Permian matters so much to our story. The mammal line was not just evolving in a general sense, it was being tested under conditions that favoured increasingly capable terrestrial bodies. The atmosphere and climate background of the late Permian also gave this world a somewhat uneasy quality. Oxygen levels and carbon dioxide concentrations shifted over geological time, and the broader Earth system was heading, though no creature could know it, toward extraordinary instability. Even before the Permian catastrophe itself, the world was not static. Environments moved, aridity expanded in many places, ecological networks adapted, strained, and reformed. One should resist the temptation to turn every ancient ecosystem into a tragedy with dramatic music behind it, but neither was this a gentle Eden. It was a hard continent-scale experiment in living. Among the most striking animals of the Permian were the therapsids, a more derived group within the synapsids and central to the story of mammalian origins. But before settling too directly into them, it is worth appreciating just how peculiar the broader cast could be. There were heavy-built herbivores with barrel chests and skulls that seemed almost overcommitted to the concept of a head. There were tusked forms, beaked forms, predators with saber-like canines, and lineages that would later branch, fade, or vanish altogether. Some looked as if nature had begun with a sensible plan and then adjusted it several times under budget constraints. Others already hinted beneath the unfamiliar surface at deeper anatomical changes that would become critically important. This is where deep time can be misleading if judged only by appearance. To a casual glance, many Permian synapsids look more reptile-like than mammal-like, and for generations that encouraged the lazy shorthand of calling them mammal-like reptiles. But that label is misleading because synapsids are not reptiles in the evolutionary sense. They are their own branch, our branch, diverging early from the lineage that would lead toward reptiles, dinosaurs, and birds. The reason they look reptile-like to us is not because they were reptiles inching toward mammalhood, but because they preserved many ancestral amniote features while also evolving new ones. Their oddity comes partly from being early versions of a design still under construction. They are not halfway between neat textbook categories. They are exactly themselves. And exactly themselves was often very successful. In many Permian communities, synapsids did not behave like marginal creatures. They were major herbivores and predators. They shaped food webs. They competed, hunted, browsed, dug, defended and reproduced across wide areas of Pangaea. If there was a dominant smell of warm, dry earth somewhere on a Permian floodplain, chances are good a synapsid was responsible for part of it. Their footprints, bones, tooth marks, and burrows tell us they were not passing through history lightly. They were participants in full. The food webs around them would have felt familiar in structure, if not in membership. Plants captured energy. Herbivores processed plant matter with varying degrees of efficiency. Carnivores targeted the herbivores or smaller vertebrates. Scavengers and decomposers broke down what remained. Seasonal stress probably created bottlenecks. Droughts would have concentrated animals around shrinking water sources. Juveniles would have been vulnerable. Competition would have been constant. The world was ancient, yes, but not dreamlike. It was ecological routine, with all the messiness that implies. One particularly useful way to think about the Permian is as a period of body experiments under pressure. Because land life had become firmly established, natural selection could now explore a wide range of solutions to recurring problems. How do you support weight on land more effectively? How do you ventilate the lungs while moving? How do you chew more thoroughly? How do you keep active when the environment shifts? How do you regulate body processes when outside conditions become unpredictable? These are not small questions, and while no single Permian animal answered them all in a fully mammalian way, the synapsid line began making serious progress on several at once. That makes the Permian feel, in retrospect, strangely modern beneath its unfamiliar surface. Not modern in appearance, certainly. You would not confuse a dicynodont with a deer, or a gorgonopsian with a wolf, unless your glasses prescription had gone terribly wrong. But modern in the sense that many of the key adaptive themes of later terrestrial vertebrate life were already being developed. Efficient feeding, more sustained activity, better control over airflow in the skull, changes in posture, and eventually more refined hearing all have roots in this older world. The stage was not waiting for mammals to invent these things from scratch. Their antecedents were already appearing. At the same time, many Permian creatures remind us that evolution is under no obligation to move in a straight line toward what we now admire. There were highly successful animals in that world whose lineages would end completely. Whole body plans flourished and disappeared. Some adaptations proved brilliant for a while, and irrelevant later. That is important because it stops us from reading history backward too neatly. We know mammals eventually succeeded, so it is tempting to imagine the Permian as obviously preparing for them. But to a Permian observer, had such an observer been both scientifically trained and remarkably difficult to alarm, there would have been no reason to assume that the future belonged to small, warm-blooded insectivores and their descendants. Plenty of other forms looked established, effective, and in no immediate danger of surrendering the world to anything else. The atmosphere of that age, then, was one of diversity without familiarity. The main roles in the ecosystem existed, but the actors wore different faces. Predators were not theropod dinosaurs or mammalian carnivores. Herbivores were not ungulates or duck-billed grazers. Even the rhythms of the land differed because the vegetation, climate patterns, and continental layout were all arranged otherwise. This mattered for our lineage because the pressures acting on early synapsids were not the pressures of later worlds. Their traits emerged in response to Permian problems. The solutions they found only later turned out to be useful building blocks for mammals. There is something quietly sobering in that. We often like origin stories to look purposeful. We want the first steps toward ourselves to feel noble or at least recognisable. Yet the real beginnings of our deep ancestry were embedded in a world full of animals that, by modern standards, seem awkward, severe, and only partially assembled. The road to mammals was not paved with charm. It was paved with practicality. Better chewing is not glamorous. Stronger jaw musculature does not usually make posters. A secondary palate will never quite compete with a dinosaur skeleton for public affection. And yet those are the sorts of details that changed everything. The Permian world also imposed a certain seriousness through scale. Pangaea was so large that regional ecosystems could be extensive, and shifts in climate or vegetation could have sweeping consequences. Animals adapted not just to one little valley, but often to broader environmental regimes. The interior dryness of the supercontinent likely favoured traits associated with water conservation, more efficient terrestrial locomotion, and bodies that could manage heat and activity without constant dependence on wet refuges. Those pressures did not instantly produce mammalian physiology, but they may have nudged the lineage in directions that later became fundamental. And still, for all this talk of systems and traits, the day-to-day reality remained simple in the oldest biological sense. Find food, avoid being eaten, reproduce if possible, repeat until geology intervenes. A juvenile synapsid sheltering from midday heat did not know it carried a small piece of a future mammalian blueprint. A predator with differentiated teeth was not anticipating the descendants who would someday use related anatomical principles to chew salad, crack seeds, hunt antelope, or complain about popcorn kernels. Evolution proceeds without foresight. That is why its grand results can feel so improbable later. By the close of the Permian, though, the world of these stranger things had become not only distinctive but fragile. The ecosystems were rich, but they were not invulnerable. Behind the ordinary struggles of drought, feeding, mating, and predation, the planet itself was edging toward a crisis of terrifying scale. Volcanism, climate disruption, ocean chemistry changes, atmospheric instability, and cascading ecological collapse would soon bring many of these lineages to the edge or over it entirely. The animals that dominated the land would not keep it by right. They would be tested by forces far beyond the usual pressures of daily selection. And that is one reason it matters to look carefully at the world before the catastrophe arrives. It lets us see just how much was already there to be lost. Not a crude preliminary sketch, but a full living world. Not an empty waiting room for dinosaurs, but a functioning planet occupied by highly specialised animals, among them the very lineage in which the first real foundations of mammal life were taking shape. The stranger things of the Permian were not failed curiosities. They were the living context in which our deepest biological inheritance began to acquire form. From there, the next step is to look more closely at one of the most important divisions in vertebrate history. Because once you understand how early amnities split, and why one of those branches carried a distinctive skull pattern and a very different future, the outline of our own story starts to sharpen. To see why the Permian matters so much to our own story, we need to look at a division that happened much earlier, long before mammals, long before dinosaurs, and long before the land was ruled by the kinds of animals people usually imagine when they think of deep prehistory. It was not a dramatic event in the everyday sense. No mountain split open to announce it. No creature stood on a rock and declared a new age. It was simply one branching in the evolutionary tree, one separation among early amniotes. And yet it changed the history of vertebrate life so profoundly that everything from crocodiles to sparrows to whales to human beings eventually ended up on one side or another of its consequences. That split was between the line that would lead towards synapsids and the line that would lead toward the therapsids, the broad group that includes reptiles in the evolutionary sense, along with dinosaurs and birds. If those names feel a little technical, the practical point is straightforward enough. Among early land vertebrates that had solved the major problem of reproducing away from water, one branch began heading toward the great reptile and dinosaur story, while another began heading toward the mammal story. And that second branch, the synapsid one, is ours. This matters because it corrects a very common mistake in the way people imagine early vertebrate evolution. There is a tendency to assume mammals somehow emerged out of reptiles as a later improvement, as if the world first produced reptiles, then one especially ambitious reptile line gradually upgraded itself into mammals. That is not how the tree works. Mammals did not evolve from reptiles in the strict evolutionary sense. Mammals and reptiles share a more distant amniote ancestry, and from that common stock the branches separated early. Once that split happened, each side followed its own long and complicated path. So when we talk about our deep ancestors in the Permian, we're not talking about reptiles on the verge of becoming something else. We're talking about members of a separate lineage that had already taken its own direction. To understand why this split mattered, it helps to start with the amniotes themselves. Before amniotes, vertebrate life on land was still tied closely to water in one major way: reproduction. Amphibian-style ancestors could move onto land and spend much of their adult life there, but their eggs and early development usually depended on moist environments or open water. That is a serious limitation if you're trying to occupy dry interiors, seasonal uplands, or any place where standing water is unreliable. The amniotic egg and the associated reproductive adaptations change that completely. With a protected embryo, specialized membranes, and a self-contained developmental environment, early amniotes could reproduce away from ponds and swamps. In practical terms, that opened up the continents. This was one of the great turning points in vertebrate history. Life on land no longer had to keep one foot permanently in the water. Once that barrier weakened, natural selection could begin refining terrestrial bodies in earnest. Posture, skin, breathing, feeding, growth, and sensory systems all came under the pressure of a more fully land-based existence. And within that early radiation of amniotes, different body plans and strategies began to diverge. At first glance, the animals may not have looked dramatically different. They were all still relatively early in the story, and many retained plenty of ancestral features. But one of the most important clues to their divergence lies in the skull. Paleontologists often classify major early amniote groups, partly by the number and arrangement of openings behind the eye socket in the skull. These openings are called temporal fenestrae, which sounds rather grand for what are in essence useful holes, but the word matters less than the function. Skull openings create space for jaw muscles and can change the way those muscles attach and operate. That means they affect biting power, feeding mechanics, and the overall architecture of the head. So these holes are not trivial details for specialists to fuss over in dusty drawers. They are important structural features tied to how an animal lives. The synapsids, our branch, are defined by having a single temporal opening low on each side of the skull behind the orbit. Sauropsids followed different arrangements, and later diapsids, the line including dinosaurs, crocodilians, lizards and birds, developed two such openings on each side. Those differences may sound narrow at first, but they reflect deeper anatomical and functional divergence. The synapsid skull pattern allowed for changes in jaw musculature that would become very important in the long evolution of stronger bites, more efficient chewing, and eventually the highly specialised jaw system of mammals. If this seems like a lot of importance to place on skull openings, that is because the head is where some of the most consequential evolutionary work happened in our lineage. Mammals are, in many ways, head specialists. We chew food in a complex way. We have differentiated teeth that perform distinct functions. Our hearing depends on tiny middle ear bones derived from much older jaw elements. Our skull architecture supports active feeding, precise occlusion of teeth, and a great deal of sensory sophistication. None of that appeared overnight. The early synapsid condition was not the final mammalian arrangement, of course, but it was the branch point from which that line of anatomical reworking became possible. Now, it is worth being careful here. The first synapsids did not look remotely like modern mammals. They were not fuzzy little prototypes scampering around with whiskers and opinions. Many were sprawling, heavy-bodied animals whose overall shape still reflected very old amniote ancestry. But lineage is not about resemblance alone. It is about relationships. And once the synapsid branch separated from the sauropsid one, the long process that would eventually yield mammalian anatomy was underway, even if the early stages looked strange to modern eyes. There is a broader lesson in that. Evolutionary history is not a ladder of visible improvements. It is a branching tree of inherited structures being modified in different ways. Early synapsids did not need to look like mammals to matter to mammal origins. They only needed to belong to the branch in which certain changes could accumulate. Over tens of millions of years, that branch would experiment with jaw mechanics, dentition, posture, respiration, metabolism, and sensory systems in a direction increasingly distinct from the sauropsid line. The initial split made those later pathways possible. The contrast becomes clearer when you consider how differently these great branches eventually solve the problem of being terrestrial vertebrates. Sauropsids, especially through the diapsid line, produced a tremendous variety of successful forms. They gave rise to marine reptiles, pterosaurs, dinosaurs, crocodilians, lizards, snakes, and birds. Their skull and jaw designs, limb arrangements, growth patterns, and metabolic strategies diversified enormously. Synapsids, meanwhile, went their own way. Their story led through the pelycosaur-grade forms into therapsids, cynodonts, true mammals, and eventually the extraordinary mammalian radiation we know today. Both branches were successful. Both were ancient, but they were not stages of one another. They were sister histories. That is why this early split changed our story so completely. It determined which anatomical experiments became available to our ancestors and which did not. It placed our lineage on a path where the lower jaw would eventually simplify into a single dentary bone, while other bones from the ancestral jaw joint would be repurposed into the middle ear. It set up the skull and muscle arrangement from which stronger and more controlled chewing could evolve. It opened a route toward heterodont dentition, meaning teeth of different shapes and functions. It helped shape the feeding efficiency that later supported higher activity levels and the energetic demands of more mammal-like physiology. At the time, of course, none of this would have been visible as destiny. The first split did not come with a sign pointing toward human beings. It was simply one divergence among early amniotes in a world full of evolving lineages, all facing the ordinary pressures of survival. But from our perspective, looking backward with the benefit of fossils and comparative anatomy, it was one of the foundational moments in our deep history. It separated the branch that would someday produce apes, elephants, shrews, and whales from the branch that would someday produce turtles, crocodiles, eagles, and non-avian dinosaurs. There is something useful in thinking about how early this happened, because it forces us to adjust our sense of scale. The mammal line did not begin shortly before mammals appear in the fossil record. It began far deeper, at a stage when the animal world still looked very unlike the later Mesozoic scenes most people know. By the time dinosaurs entered the story, the synapsid-sauropsid split was already ancient. Our lineage had already been evolving separately for a very long time. This is also where the familiar museum confusion around animals like Dimetrodon becomes more instructive than embarrassing. Dimetrodon is often grouped in the public imagination with dinosaurs because it is large, prehistoric, and has a dramatic silhouette. But Dimetrodon is a synapsid, not a dinosaur, and it lived millions of years before the first dinosaurs existed. That means one of the most recognizable animals from ancient terrestrial ecosystems actually belongs, in the broadest lineage sense, closer to us than to Tyrannosaurus. Not close in a sentimental sense, naturally. You would not want to invite either one indoors, but close in terms of branching history. That fact helps undo the old habit of treating everything ancient and scaly looking as vaguely reptilian. Deep time does not care about our visual shortcuts. Evolutionary relationships are not judged by whether an animal resembles the toy aisle. A sprawling synapsid with a sail can still be on our side of the split. A sleek bird with feathers can still be a surviving dinosaur on the other side. Once you accept that, the early amniote tree starts to make more sense, and the Permian begins to look less like a strange prelude and more like a key part of our own background. The anatomical importance of the split becomes even clearer if we look more closely at feeding. In early vertebrate evolution, feeding systems place strong constraints on lifestyle. The way an animal bites, tears, crushes or grinds food shapes its ecology. Synapsids, from fairly early on, show trends in skull and jaw organisation that would later support more powerful and more refined feeding. The single temporal opening allowed expansion of certain jaw muscles and changes in muscle orientation. Over long time spans, this contributed to the increasingly complex jaw function seen in later therapsids and cynodonts. Mammals inherit the end result of that history, a jaw system capable of precise tooth occlusion, sustained chewing, and efficient food processing. That might sound less exciting than discussing giant predators, but in evolutionary terms it is tremendously important. Efficient chewing allows more thorough mechanical breakdown of food. That can support higher metabolic demand because nutrients become easier to access. It can also shorten the time needed to process food in the gut, influence skull design, and expand dietary flexibility. When you think about mammals as active animals with demanding physiologies, remember that much of that story begins in the head. And the head in our lineage started taking a distinctive route from the moment the synapsid branch separated. There's also a practical ecological angle. A lineage that becomes better at processing food can explore niches in different ways. Herbivory becomes more efficient if plant matter can be reduced thoroughly. Carnivory becomes more specialised if teeth and jaw muscles support slicing, puncturing, or holding prey more effectively. Omnivory becomes possible in broader form if dentition can be diversified. The first split did not instantly create such ecological flexibility, but it placed the lineage on the road toward it. At the same time, we should resist the urge to make the split sound too clean or too rapid. Evolutionary branches do not begin with a fully formed identity. Early synapsids still shared many ancestral traits with other early amniotes. Their limbs were often sprawled. Their gait was not yet the more upright posture associated with many later forms. Their skin, growth patterns, and physiology were not those of modern mammals. What changed first was the branching relationship in a set of structural tendencies. The fully mammalian package emerged much later, through many intermediate stages. That gradualness is important because it reminds us how deep and patient this process was. We're not talking about a quick transition from one body plan to another. We are talking about tens of millions of years of cumulative modification. The first split is significant not because it completed the job, but because it established the branch in which the job would be done. It is the difference between stepping onto one road or another at the start of a journey so long that most of its travellers would never glimpse the destination. There is another reason this split changed our story, and it has to do with extinction and survival. Once lineages diverge, they do not merely accumulate different traits. They also face different risks and opportunities through geological time. The synapsid line would become extraordinarily important in Permian terrestrial ecosystems, then suffer catastrophic losses at the end Permian extinction, then recover through a much narrower surviving branch that eventually produced mammals. The sauropsid line, meanwhile, would generate the diapsid radiation that flourished spectacularly in the Mesozoic. If our lineage had been on the other side of that early split, there would be no mammals as we know them. There would be some other story entirely, perhaps equally interesting, but it would not include us. And that brings us back to the strange balance between inevitability and contingency in evolution. The first split feels foundational in retrospect because we know what came later, but it was not inevitable that the synapsid branch would survive what lay ahead. It was not inevitable that mammal traits would accumulate as they did. It was not inevitable that one small branch would pass through the Permian-Triassic bottleneck and continue. The split created possibility, not guarantee. That is one reason it deserves attention. It is the beginning of our branch, but only the beginning. Everything after it still had to be one. If you imagine the history of terrestrial vertebrates as a vast braided river, then this was one of the moments when the current carrying our future diverged into its own channel. At first, the difference may not have seemed dramatic. The water still flowed across the same floodplain of early amniote life. But as time passed, the channels deepened and their courses separated. One would carry the lineage toward therapsids, cynodonts, mammals, and eventually human beings capable of reconstructing the whole affair from bones and sediments. The other would carry the lineage toward the reptiles and birds that have their own equally impressive history. Both belong to the same larger story of life on land, but they are not the same stream. So when we say this was the first split that changed our story, we're not giving special treatment to some arbitrary taxonomic detail. We are identifying the branching point that made mammalian evolution possible as a distinct enterprise. It is the reason our ancestors, however strange they looked, were already separate from the ancestors of dinosaurs long before dinosaurs appeared. It is the reason the key features that would later define mammals began to assemble in our own deep branch, rather than being borrowed second-hand from another. And it is the reason that when we go looking for the foundations of ourselves, we do not begin after the age of dinosaurs. We begin here with early amniotes, skull architecture, and a lineage taking shape in quiet separation. From there, the next step is to follow that branch into the animals that first made it visible on land in a major way, because once synapsids began to spread and diversify, the distinct future of our lineage started to acquire real anatomical substance. By the time the synapsids begin to matter in a big way, the story has already moved beyond that first quiet split in the amniote family tree and into something far more visible. A branch that had once differed mainly in skull structure was now becoming a major presence on land. And this is where the usual picture of our ancestry starts to come apart in a useful way. Because if you have been taught to imagine the ancestors of mammals as small, timid little creatures waiting patiently for dinosaurs to vanish, synapsids are here to ruin that idea quite thoroughly. For long stretches of the Permian, the lineage that would one day lead to mammals was not hiding. It was large, diverse, ecologically important, and in some places among the dominant forms of terrestrial vertebrate life. That does not mean synapsids looked like mammals in any modern sense. They did not. Most of them would look deeply strange to us, and several would probably strike the average observer as if nature had been given a box of vertebrate parts and told to improvise under difficult conditions. But lineage is not a matter of charm or resemblance, it is a matter of descent. And once synapsids began to diversify, they became the main stage on which the earliest real foundations of mammalian anatomy and physiology would be built. The word synapsid itself can sound rather clinical, but what it marks is one of the most important long-term branches in vertebrate history. These animals were the descendants of that early amniote split, and over time they developed in ways that increasingly set them apart from the sauropsid line. In the beginning, they still retained many ancestral features. Their bodies were often sprawling, their skulls could be heavy and broad, their movement was not yet the more efficient, fully upright style associated with many later animals. Yet even among the earlier forms, especially the so-called pelycosaur-grade synapsids. The distinctive root of our lineage was starting to show itself. Some of these early synapsids are famous mainly because they are so often misidentified. Dimetrodon is the classic case. It turns up in toy sets, picture books, murals, and children's conversations about dinosaurs despite not being a dinosaur at all and having the courtesy to live tens of millions of years before the first dinosaur arrived. This confusion is so common that paleontologists have probably developed a special facial expression for it, a mixture of patience, mild suffering, and the awareness that they are about to explain temporal fenestrae again. But the mistake is useful because it reveals how strongly modern people sought ancient animals by appearance rather than by relationship. Dimetrodon looks old, large and dramatic, so it gets swept into the dinosaur pile. In reality, it belongs to the synapsid lineage, which means that in broad evolutionary terms it stands closer to mammals than to dinosaurs. That does not make Dimetrodon our direct ancestor, and it certainly does not make it mammal-like in the cozy sense. It was still a heavily built predator with a sprawling posture and a skull designed for a very different life from ours. But it shows that the synapsid line was already experimenting with size, feeding specialization, and ecological dominance early on. These were not marginal creatures in forgotten corners. They were major players in Permian ecosystems. The early synapsid world included both predators and herbivores, and this matters because it tells us the lineage was not narrowing toward one clever trick. It was radiating into different roles. Some species developed powerful jaws and sharp teeth suited to active predation. Others evolved broader bodies and feeding adaptations for processing plant material. The fact that synapsids could diversify this way suggests that their branch was not just surviving, but flourishing under Permian conditions, and flourishing means selection has room to work. A lineage spread across many ecological roles can be tested in many ways. Different diets, climates, body sizes, and behaviours all create different pressures, which means more opportunities for useful anatomical changes to appear and persist. One of the first things to appreciate about synapsids is that they were not a single uniform design. They were a broad and changing collection of forms, and over time their descendants would become even more varied. The earlier pelycosaur-grade synapsids included animals with sprawling bodies and relatively simple limb arrangements, but already the skull tells a more interesting story. The single temporal opening behind the eye socket allowed jaw muscles to expand and reposition in ways that could support stronger bites and more sophisticated feeding mechanics. That may sound like a small detail, but in evolutionary terms it is foundational. Feeding is one of the great organising problems of vertebrate life. If you can bite better, chew better, process food better, and exploit resources more effectively, a great many other possibilities open up. This is where synapsids begin to reveal that they were the lineage with a different future. They were not just another set of Permian vertebrates doing Permian things until something better came along. They were the branch in which the head was being reorganized for a more intensive relationship with food. Later mammals would take this to an extraordinary degree. They would develop precise occluding teeth, strong jaw musculature, and a single lower jaw bone bearing the full functional bite, with old supporting bones reassigned to hearing. But that later sophistication has roots in the synapsid condition. It begins with a different way of building the skull. The Permian environment likely helped to make such improvements important. Life on land in the interior of Pangaea was not especially generous. Plants could be tough and dry, water could be seasonal. Activity levels were shaped by heat, drought, and competition. A body that handled feeding more efficiently had a genuine advantage. Carnivores benefited from stronger bites and better prey handling. Herbivores benefited from teeth and jaws that could do more than simply seize and swallow. The old amniot toolkit was being modified under pressure, and synapsids were one of the main groups in which those modifications accumulated. As time went on, the synapsid story did not remain at the pelycosaur stage. More derived forms began to appear, especially the therapsids, and with them the branch leading toward mammals took on clearer direction. But even before getting there, It is worth noticing that the earlier synapsids already show how evolution works through mosaics, rather than sudden transformation. A body may retain a sprawling posture while the skull becomes more specialised. Teeth may begin to differentiate while limb mechanics still seem old-fashioned. A feeding system may become more advanced before posture or metabolism follows. That unevenness is not evidence of confusion. It is how deep evolutionary change usually proceeds. Nature does not wait for a complete redesign before improving part of the machinery. There is also an important ecological point here. The lineage leading toward mammals did not earn its future by being cute, small, or overlooked. In many Permian ecosystems, synapsids were large-bodied and abundant. Some dominated herbivorous niches, others were apex predators. This matters because it reminds us that mammalian ancestry was not originally a side business. Our branch was, for a while, one of the main terrestrial experiments of its age. Later, after catastrophe and narrowing survival, mammals would become small and marginal through much of the dinosaur age. But that comes later. In the Permian, synapsids often lived in the centre of events. This makes the eventual shape of our lineage even more striking. The ancestors of mammals were not always tiny nighttime survivors. At one stage, their broader branch included some of the most important land vertebrates on Earth. Then much of that diversity was nearly erased. The branch that finally gave rise to mammals was a reduced surviving remnant of something once much broader and more commanding. So when we look at synapsids, we are looking not just at the beginnings of mammalian traits, but at the remains of a lineage that had a much larger early career than most people realise. The therapsids, which emerge from within the synapsid line, are especially important because many of the traits associated with later mammals begin to sharpen there. Compared with earlier synapsids, therapsids often show more advanced jaw musculature, more differentiated teeth, changes in posture, and shifts in skull design that point toward more active and efficient lifestyles. They are still not mammals, and one should not mentally dress them in fur and hand them modern habits too quickly. But they are clearly moving in a direction that matters to us. Their bodies are beginning to solve terrestrial life in ways that would prove central later. It is also in the therapsid radiation that the synapsid lineage becomes visibly more varied in its strategies. There were herbivorous therapsids built for consuming large quantities of vegetation, some with beak-like mouths or tusks, others with heavy bodies and deep chests. There were also predatory forms, including the gorgonopsians, with large saber-like canines and skulls clearly specialised for seizing prey. If you encountered one in the Permian, you would not leave with the impression that the mammal line was a modest, retiring affair. These were formidable animals in their own environments, and yet, beneath all that diversity, the important part for our story is not which one looked most impressive. It is which anatomical trends were taking hold. Teeth were becoming more specialised. Jaw muscles were becoming more powerful and differently arranged. The lower jaw was beginning a long journey toward simplification. The secondary palate, which allows breathing and chewing to be better separated, was beginning to appear in more developed form in some later synapsids and therapsids. Posture was beginning in certain groups to shift away from a full sprawl towards something that placed the limbs more effectively beneath the body. None of these changes instantly made an animal mammalian, but together they point to a lineage working toward more sustained activity, more efficient feeding, and better control over the body's interactions with the environment. If that sounds like the early outline of mammal success, that is because it is. Mammals are in many ways specialists in sustained terrestrial performance. They chew food thoroughly. They ventilate efficiently. They hear with unusual sensitivity. They regulate their internal conditions in demanding ways. They can remain active across wide temperature ranges and behavioural contexts. Not every mammal is impressive at all of these all the time naturally. Some have chosen lives of admirable laziness. But the broader mammalian pattern depends on a suite of anatomical and physiological traits whose roots lie in synapsid history. This makes synapsids unusual in another sense. They are not simply ancestors in the genealogical meaning of the term. They're also the setting in which major mammalian solutions first began to assemble. A lineage can survive for millions of years without changing the larger logic of its design very much. Synapsids did not do that. Over time, they became a laboratory of structural experimentation. Not a planned laboratory, certainly. Evolution is not tidy enough for that. More like a long-running field test in which better ways of feeding, moving and processing the world gradually accumulated because they worked. The skull remains central here. One of the great themes of synapsid evolution is that the mammalian head did not appear suddenly. It was built through repeated modifications of ancestral parts. The lower jaw in early synapsids still included multiple bones, as in other early amniotes. The jaw joint itself was not yet the mammalian one. Over immense spans of time, however, one bone in the lower jaw, the dentary, became larger and more dominant, while the others shrank and changed role. Eventually, in true mammals, the dentary alone bears the lower jaw and articulates with the squamosal bone of the skull, forming a new jaw joint. The old articular and quadrate bones, once part of the ancestral jaw joint, became two of the middle ear ossicles, the malleus and incus. That transformation is one of the most remarkable pieces of anatomical repurposing in vertebrate history, and it begins deep in the synapsid line. What is so satisfying about this story is that it is both very technical and very humanly interesting. It is about bones moving from one job to another over evolutionary time, but it is also about why mammals hear the way they do, why our chewing is so effective, why the architecture of our faces and skulls is what it is. The head you carry around now, ideally with some rest inside it, has a history that runs back through synapsid experiments in muscle attachment, dentition, and jaw construction. Long before primates, long before mammals, long before anything remotely resembling us, the basic problem of how to build a more efficient vertebrate head was already being worked on. Another reason synapsids deserve more attention is that they remind us how misleading labels can be. For many years, especially in older popular writing, synapsids were often called mammal-like reptiles. That phrase was meant to be helpful, but it has caused no end of trouble because it suggests that reptiles are the main category and mammals came out of them later by gradual improvement. In reality, synapsids are not reptiles in the evolutionary sense. They are a separate branch. The reason they look reptile-like to modern eyes is simply that both lineages began from early amniote conditions, and many ancestral features were retained for a long time. But similarity in general body shape is not the same thing as relationship. Calling synapsids reptile-like is a little like calling your great-great-grandparent modern-like but less convenient. It says something, but not the most useful thing. What makes synapsids the lineage with a different future is not just that they were our ancestors, it is that they carried a different set of long-term anatomical possibilities. Once their branch separated, their descendants began modifying inherited structures in ways that would later support mammalian life. They were not heading toward dinosaur-style success. They were heading towards something else, though that something else would pass through many forms that looked nothing like the final outcome. It is also worth noticing that this different future was not obvious at the time. If you had surveyed the Permian world without the benefit of hindsight, you might have seen synapsids as highly successful animals, but not necessarily as the eventual foundation of a lineage that would outlast dinosaurs and produce technologically overconfident primates. Many other groups looked successful too. Evolution rarely signals in advance which branch will prove durable after the next catastrophe. Synapsids became important not because their future was guaranteed, but because enough of their anatomical innovations remained useful through changing worlds. And changing worlds are the essential part of the story. A lineage's future is not determined in stable conditions alone. It is determined by whether its traits continue to function when environments shift, climates become harsher, food webs collapse, and competitors change. Synapsids developed in the Permian under one set of conditions, but the branch that would later give rise to mammals had to pass through the greatest extinction event in Earth history and survive the ecological reorganizations that followed. The future written into the synapsid line was not a reward, It was a narrow continuity through disaster. That is why, when we look back at synapsids, we should see both their strength and their vulnerability. They were successful enough to dominate many terrestrial ecosystems. They were innovative enough to begin reworking the vertebrate body in profoundly important ways. But they were not immune to extinction, and much of their diversity would be lost. The lineage with a different future did not keep all its options. It kept only enough. Still, enough was enough. Out of synapsid history came therapsids, and from therapsid history came the more advanced synodonts, and from within those lineages eventually came true mammals. So when we ask where the mammalian story really begins, the answer is not with the first unmistakable mammal in the fossil record. It begins here, in the synapsids, where the branch first started behaving like a lineage with its own long-term plan, even if evolution itself had no plan at all. From that point onward, the details become even more interesting, because once therapsids enter the picture, the mammal-building process becomes clearer in the anatomy itself. Teeth become more specialised, jaws more efficient, breathing better coordinated, posture more capable, and the old skull begins to reorganise in ways that bring the future a little closer. Once synapsids had established themselves as a major branch of life on land, the next important change was not a sudden leap into mammals, but a long period in which the branch began reorganising itself in ways that would later matter enormously. This is where therapsids enter the story. They evolved within the synapsid lineage during the Permian, and by the middle to late Permian they were a dominant part of terrestrial ecosystems. They were not mammals yet, and they were not a neat halfway category either. They were a diverse radiation of non-mammalian synapsids, in which many of the anatomical trends that later define mammals became clearer and more concentrated. In other words, if early synapsids open the door, therapsids are where the house starts getting framed. It helps to be careful with the mental picture here, because therapsid can sound like the name of one specific creature, perhaps something grey, toothy and permanently annoyed. In reality, therapsida includes a broad range of forms. There were large plant eaters, active predators, tusked specialists, barrel-bodied herbivores, saber-toothed hunters, and eventually the more advanced theridonts and synodonts that sit much closer to mammals. The important point is not that all therapsids looked similar. It is that across this radiation, the synapsid head, jaw, teeth, and body plan were being repeatedly modified in ways that would make later mammals possible. The change was gradual, uneven, and spread across millions of years, but it was real. One of the clearest places to see this is in the teeth. Mammals are famous for heterodonty, meaning different teeth doing different jobs. Incisors nip, canines seize or puncture, and cheek teeth slice, crush, or grind depending on the species. That sort of specialization does not suddenly appear with the first true mammals. It develops gradually in therapsids and becomes especially pronounced in synodonts, where the teeth and jaws show increasing functional differentiation and more complex occlusion. Paleontologists pay so much attention to teeth, partly because they fossilize well, but also because they record feeding strategy with wonderful stubbornness. When a lineage starts dividing the mouth into different tools for different tasks, it usually means feeding efficiency is changing in a serious way. That improvement in feeding matters more than it may sound at first. A more specialised dentition lets an animal process food more thoroughly before swallowing it. For a carnivore, that can mean better control over prey and more effective slicing. For a herbivore, it can mean breaking down tough plant material more efficiently. For a small active animal, it can mean extracting more usable energy per meal. Over evolutionary time, that kind of efficiency is not just a convenience. It changes what sorts of lifestyles become possible. It supports higher activity, more flexible diets, and eventually the energetic demands associated with more mammal-like physiology. Better chewing is not especially glamorous, but evolution has rarely cared whether a breakthrough sounds glamorous to a modern audience. At the same time, the jaws themselves were being reworked. Early amniotes, including early synapsids, had lower jaws made of several bones. Mammals are different. In mammals, the lower jaw is composed of a single main bone, the dentary, and the jaw joint is formed between the dentary and the squamosal bone of the skull. That distinctive mammalian arrangement did not arrive all at once. Through therapsid and especially synodont evolution, the dentary became progressively larger and more dominant, while the post-dentary bones shrank in relative importance. The arrangement of the jaw muscles also changed, improving bite control and strength. This is one of the central structural trends in mammalian origins. The feeding apparatus is being simplified in one sense and refined in another. That same process also set up one of the most extraordinary reorganizations in vertebrate anatomy. The bones that once helped form the ancestral jaw joint did not simply disappear. In the mammalian line, the articular and quadrate were eventually repurposed into two of the middle ear ossicles, the malleus and incus, while the stapes was retained as the third ossicle. This means that part of the mammalian hearing apparatus is literally inherited from the jaw mechanism of earlier synapsids. The fossil record, comparative anatomy, and developmental biology all support this transformation. Advanced synodonts and early mammalia forms show transitional arrangements in which the dentary squamosal joint is taking over, while the older post-dentary elements are reduced and increasingly associated with sound transmission. It is one of the best documented examples of major evolutionary repurposing anywhere in the vertebrate skeleton. This is where therapsids start to feel less like a distant curiosity and more like a necessary part of our own physical history. The way mammals hear high-frequency airborne sound, the way our lower jaw works, and the very shape of the side of our skull all depend on a long anatomical transition that runs through therapsids and synodonts. You could say, without being at all dramatic, that part of the mammalian face was invented here. Not completed, naturally. Nature is not usually kind enough to finish anything in one go, but invented in the sense that the pieces were being separated, enlarged, reduced, and reassigned in a direction that later mammals would inherit. Another important development was the secondary palate. In mammals, the bony secondary palate separates the nasal passage from the oral cavity, which lets an animal breathe while chewing. That may not sound revolutionary until you imagine trying to process food vigorously while repeatedly interrupting your own airflow. A full mammalian palate appears late in the story, but forms of secondary palate evolved in several therapsid groups, and in synodonts it becomes especially important. Researchers have long linked this structure to more efficient respiration, and possibly to increased metabolic demands. It is not a magic switch for warm-bloodedness, and one should be cautious about pretending a single bone arrangement can settle every physiological question. But it is one of the strongest anatomical signs that the mammalian line was becoming better at sustained oxygen intake, while feeding and moving. That question of metabolism sits quietly behind much of therapsid evolution. Mammals are endothermic, meaning they generate and regulate a significant amount of body heat internally. Figuring out exactly when and how endothermy evolved is difficult, because warm blood does not fossilize, and ancient animals were inconsiderate enough not to leave behind little metabolic instruction manuals. But multiple lines of evidence suggest that mammalian-style endothermy arose stepwise rather than appearing fully formed in a single moment. Bone histology, isotope data, respiratory structures, posture, and cranial anatomy all suggest that aspects of elevated metabolism were developing through therapsid and early synodont evolution, with important advances around the late Permian and early Triassic. In other words, the body was being rewritten gradually. There was no single morning when a therapsid woke up and announced, to nobody in particular, that it had become warm-blooded. Part of that rewriting involved the way therapsids stood and moved. Earlier synapsids often had a more sprawling posture, with limbs projecting out to the side in a way that made locomotion workable, but less mechanically efficient for sustained activity. In various therapsid groups, and more strongly in later forms closer to mammals, the limbs begin shifting toward a more upright, or at least less fully sprawling arrangement. The exact path was not uniform across all lineages. and one should avoid speaking as though every therapsid marched steadily toward modern mammalian posture. They did not. But the broad trend matters. A more upright stance can improve efficiency in locomotion, reduce side-to-side body flexion during movement, and work better with the kind of continuous breathing associated with more active lifestyles. This matters because sprawling locomotion can interfere with effective ventilation, especially during prolonged running. Mammals eventually solve this problem much more cleanly. Therapsids begin pushing in that direction. Cynodonts are especially important here because they sit close to the origin of mammals and preserve a striking mix of ancestral and advanced features. Their craniodental anatomy has been studied in detail precisely because it records the concentration of mammalian traits before true mammals appear. In cynodonts, we see further enlargement of the dentary, more complex post-canine teeth, better developed palates, and skull architecture that increasingly resembles the mammalian condition in functional terms, even when it has not yet fully crossed the anatomical line. Some advanced cynodonts also show evidence of more precise tooth occlusion and reduced patterns of replacement compared with earlier synapsids, pushing further toward the mammalian way of feeding. They are not half mammals in some vague popular sense. They are non-mammalian therapsids, in which the mammalian toolkit is becoming much easier to recognize. It is also worth noticing that the slow invention of mammal traits did not happen in a straight sequence, one neat feature after another. Evolution rarely behaves that politely. Some lineages developed strong secondary palates without becoming direct ancestors of mammals. Some experimented with specialized dentitions and then vanished. Some retained older postures while advancing in skull function. Others show mosaics of features that make sense only when you stop expecting textbook categories and start thinking in terms of branching experiments. This is one reason therapsids are so scientifically valuable. They show the assembly of mammalian traits as a distributed process. Mammalian characteristics did not arrive as a sealed package labelled "open after dinosaurs." They were accumulated in pieces across multiple therapsid and cynodont lineages, with only one surviving branch eventually carrying enough of them forward into true mammals. That broader picture also helps explain why the term mammal-like reptiles has become so unsatisfying. It encourages the idea that therapsids were basically reptiles with hints of mammal added on top, which is not how the branching history works. Therapsids are part of the synapsid lineage, and mammals arise from within that lineage. They are not evolutionary side notes to reptile history. They are the deep prehistory of mammals themselves. In that sense, saying mammals came from therapsids is not a loose metaphor. It is the actual phylogenetic relationship. Mammals are therapsids in the same broad cladistic sense that birds are dinosaurs, although I do appreciate that neither comparison necessarily improves dinner conversation unless the company is very carefully selected. The ecological setting makes all this more impressive. Therapsids were not evolving these traits in a vacuum. They were doing so while occupying real terrestrial ecosystems, competing, feeding, reproducing and surviving in the often harsh environments of the Permian and Triassic. Many were large-bodied, some were dominant herbivores, others were top predators. Then the end Permian mass extinction arrived and rewrote the rules with appalling efficiency. Most lineages vanished. Entire ecological structures collapsed. The surviving therapsid branches that made it through into the Triassic did not simply continue unchanged. They passed through a bottleneck in which only a narrow subset of the old diversity endured. Yet that subset included the forms closest to the mammalian future. And after the extinction, some of the key trends associated with more active physiology and improved locomotion appear to accelerate. Catastrophe did not create mammal traits from nothing, but it may have strongly filtered which lineages and which body plans persisted. There is something quietly remarkable in that. The features we associate with mammals were not assembled in safety. They were assembled in a lineage that came very close to being erased. Stronger chewing, better some airflow separation in the skull, a more dominant dentary, changes in posture, and the beginnings of an ear built from old jaw bones were all part of an evolutionary project that could easily have failed in the most literal sense. If the surviving therapsid and synodont branches had been lost at the end of the Permian, there would have been no mammals, no later primates, and no humans congratulating themselves for finally understanding where the ear bones came from. The slow invention of mammal traits is impressive partly because it was so precarious. And yet the invention did continue. By the time we reach the more advanced synodonts, the future feels closer. The skull is more reorganized, the teeth more specialized, the jaw more clearly dominated by the dentary, the palate more developed, and the body in some forms more consistent with sustained activity. Still, these are not true mammals yet, and that distinction matters. There remains a long difference between being on the way to a mammalian condition and actually crossing into the first mammalia forms. But the direction is unmistakable. The line is no longer just a synapsid lineage with an interesting skull opening. It is a branch whose head, mouth, and body are converging on a new functional system. This is why therapsids deserve more attention than they usually receive. Dinosaurs have the advantage of scale, drama, and very successful marketing. Therapsids, by contrast, ask you to care about the slow enlargement of the dentary and the repeated refinement of chewing surfaces. That is admittedly a harder sell at first glance. But if you care where mammals came from, therapsids are where the story turns from broad ancestry into actual construction. They are where the mammalian head begins to take shape, where the old amniote jaw starts surrendering part of itself to hearing, where feeding becomes more exact, where breathing and chewing become less mutually inconvenient, and where the body begins edging toward the energetic style that later mammals will make famous. They are not the opening note, they are the long engineering phase. So when we say that mammals were rooted deep in the Permian, this is the part of the story doing the hard work. Therapsids did not simply exist before mammals, they built much of what mammals later used. Not in one clean line, and not in one triumphant burst, but through a distributed, messy, highly successful series of anatomical revisions. By the end of that process, the head of a synodont was already telling a story that a mammal would eventually finish. And once the mouth and jaw are changing this much, it becomes impossible to ignore the next question. Because the real revolution was not only that these animals had better teeth, but that they were becoming able to use those teeth with far more force, precision, and efficiency than their earlier ancestors ever could. By the time the mammal line reached the later therapsids and synodonts, the most important work was happening in a place evolution often favours when it is being practical rather than theatrical: the mouth. Teeth, jaws, and the arrangement of the skull were being reworked in ways that changed not just how these animals fed, but how they breathed, how active they could be, how quickly they could process energy, and eventually how they would hear. The Field Museum notes that non-mammalian synapsids document the history of several hallmark mammalian features at once, including a bony secondary palate, complex tooth occlusion, upright limbs, and the incorporation of jaw bones into the middle ear. That is a surprisingly busy list for a set of animals many people still only know as those odd things before the dinosaurs. It is worth pausing on the teeth first, because teeth are one of the clearest ways evolution leaves behind its intentions without ever having had any. Early vertebrates often relied on simpler dentitions in which the teeth were broadly similar from front to back. That kind of arrangement is perfectly serviceable if your plan is mainly to seize, puncture, and swallow. But mammals do something more elaborate. They divide labour in the mouth, incisors cut, canines grip, cheek teeth shear or grind, and the upper and lower teeth meet in carefully patterned ways. Reviews of synodont and early mammalian craniodental anatomy emphasise that this concentration of evolutionary change in the skull and dentition was central to the origin of the mammalian condition, and that mammals inherited differentiated tooth classes from more advanced non-mammalian synodont ancestors. That shift from similar teeth to specialised teeth is called heterodonty, which sounds like a condition you ought to mention apologetically to a dentist. But in this case, it was one of the great innovations of our lineage. A mouth full of differently shaped teeth is not just a tidy anatomical upgrade. It is a way of turning feeding into a more controlled and efficient operation. Instead of relying on the same tooth shapes to do every job badly, the animal can use different tools for different stages of processing. That matters enormously if food is tough, fibrous, or difficult to exploit quickly. In later cynodonts and early mammalia forms, researchers describe increasingly complex post-canine teeth and more developed occlusion, meaning the upper and lower teeth meet in more precise ways during chewing. That kind of precision is not decorative. It is mechanical advantage turned into survival, and survival in these ancient landscapes was very often a matter of margins. A herbivore that could crop and reduce plant material more effectively could get more value out of each mouthful. A predator that could hold, puncture and slice prey more efficiently could waste less energy in the chase and the struggle that followed. A small active animal with better oral processing could spend less time exposed while feeding, and more time doing the equally urgent work of not becoming someone else's lunch. Modern research on mammalian dental diversity describes mammal teeth as being especially well adapted for oral processing and occlusion, while the broader Synodont review frames these craniodental changes as a major part of the transition toward mammalian biology. In other words, the architecture of survival was being assembled one bite at a time. The jaws were changing along with the teeth, and here the story becomes even more consequential. In early amniotes, the lower jaw was not a single bone as it is in mammals today. It was a more complicated structure made of multiple bones, with the jaw joint formed between the articular in the lower jaw and the quadrate in the skull. Berkeley's overview of synapsid jaw evolution explains that the earlier synapsids had that older quadrate articular arrangement, while mammals now use a different joint between the dentary and squamosal. Somewhere along the synapsid line, several groups began evolving a second pair of bones involved in jaw articulation, creating a transitional condition before the older elements lost their original role. That transitional phase is one of the most informative pieces of the whole story. What changed over time was not just the joint, but the balance of authority within the jaw itself. The dentary, the tooth-bearing bone of the lower jaw, became progressively larger and more dominant in synapsid evolution. Reviews of mammalian jaw evolution describe a broad trend toward dentary enlargement across synapsid fossils, and modern mammals represent the endpoint of that trend. A single lower jawbone meeting the squamosal in a distinct mammalian jaw joint. This was not merely a reshuffling of labels in an anatomy textbook. A larger dentary allows stronger direct support for the teeth, and more efficient transfer of force during biting and chewing. It turns the lower jaw into a more unified and robust lever, which is exactly the sort of thing natural selection notices with approval. That increase in dentary dominance also changed how the jaw muscles could be arranged and used. Work on the mammalian jaw adductor complex and the functional reorganization of the cranial skeleton emphasizes that the synapsid to mammal transition involved major rearrangement of the jaw musculature alongside the emergence of the new jaw joint. Earlier non-mammalian synapsids often relied on a feeding system in which the muscles were especially active when the jaw was open, a kind of kinetic inertial biting pattern that differs from the more refined muscle coordination of later mammals. Over time, the musculoskeletal system of the jaw became better suited to controlled closure, sustained loading, and more precise chewing. It is a reminder that a jaw is not simply a set of bones with teeth attached. It is a moving machine, and machines depend as much on force paths as on parts. This is one of the reasons the single temporal opening behind the eye matters so much in synapsids. The Field Museum notes that this opening is a shared synapsid feature around which jaw muscles attach, and it is one of the basic clues that lets paleontologists recognize the lineage in the fossil record. That opening is not a decorative gap. It is space for musculature, leverage, and reorganization. It allowed the head to be built in a way that supported stronger and more varied jaw mechanics than would later become critical for mammals. If you wanted to design a lineage that would one day chew thoroughly, process food efficiently and eventually evolve a highly specialised face and ear. Beginning with a skull already committed to reorganising its jaw musculature was a very helpful move, even if no one at the time would have appreciated the long-term significance. Chewing itself deserves more respect than it usually gets in popular prehistory. We tend to admire the dramatic parts of evolution: claws, horns, giant sails, saber teeth, and all the features likely to end up painted on a lunchbox. But mastication is one of the quiet superpowers of mammals. Thorough oral processing breaks food into smaller pieces before it reaches the gut, which increases the surface area available for digestion and can make energy extraction more efficient. The Synodont Craniodental Review and broader work on mammalian cranial evolution both point to dental occlusion and specialised tooth form as central steps in this broader transition. A lineage that can reduce food more effectively in the mouth, can support different digestive strategies, maintain higher activity levels, and potentially reduce the amount of time spent vulnerably feeding. It is not glamorous, but neither is a well-designed bridge, and both are much easier to appreciate when they fail. There is also an ecological side to this. Teeth and jaws are where lifestyle becomes visible in bone. A broad-snouted herbivore with expanded cheek teeth is making one sort of living. A predator with enlarged canines and slicing surfaces is making another. Reviews of non-mammalian synapsid ecomorphology show increasing bite diversity across predatory synapsids, while the broader synapsid record captures repeated experimentation in feeding ecology. This variety matters because it means the mammal line was not moving toward one single diet or one specialised way of life. It was building a toolkit. Once you have a head that can be modified towards slicing, crushing, grinding, nipping, or mixed feeding, a great many ecological doors become available. Evolution likes tools that can be repurposed. The synapsid jaw turned out to be one of them. As the dentary expanded and the jaw joint changed, an even stranger consequence followed. The older bones at the back of the ancestral jaw did not simply vanish once they became less important to biting. Berkeley's summary explains that after transitional synapsids evolved the new dentary squamosal articulation, the quadrate and articular gradually lost their role in jaw function, became smaller, and moved into the ear region, where they became the malleus and incus. Reviews of mammalian middle ear evolution describe this connection between the novel jaw joint and the three-ossicle as one of the best documented transformations in vertebrate anatomy. So while the jaw was becoming better at chewing, part of it was also being freed up for a new job in hearing. That is not just economical evolution, that is borderline architectural genius, achieved entirely without conscious design. The two changes were connected. The same broad reorganisation that made the lower jaw more efficient for biting and chewing also made it possible for the old post-dentary bones to become smaller and less load-bearing. Once the dentary squamosal joint could take over the main mechanical demands of feeding, the ancestral jaw elements no longer had to remain large support structures. Reviews of jaw joint evolution describe the mammalian temporomandibular joint as a novel structure that evolved together with the middle ear, not independently from it. That is an important correction to the idea that evolution simply added a better ear later. It did not. The ear and the jaw were disentangled together. One part became more specialised for chewing, and another became more specialised for transmitting sound. In evolutionary terms, this was not one upgrade. It was a coordinated renovation. There is something wonderfully practical about that. Mammals eventually became animals that are very good at two things rarely combined so elegantly in earlier vertebrates. They chew thoroughly, and they hear extremely well. The American Museum of Natural History notes that the modern mammalian middle ear, with its 3 bones, gives mammals the sharpest hearing on Earth, while reptiles and birds retain a single middle ear bone. The museum's 2024 coverage of new Jurassic fossil mammals emphasises that tooth, jaw and ear evolution are deeply entangled in early mammal history. The message is plain enough. The same region of the head that was being optimised for food was also being reorganised for sound. A face was becoming more competent in multiple directions at once. That helps explain why the mammalian head feels so different from that of other tetrapods. It is not only more specialised, it is more internally divided in its labour. The jaw is concentrated into a strong dentary squamosal mechanism. The teeth are differentiated and often precisely occluding. The old post-dentary elements are no longer trying to help with chewing and hearing at the same time. The secondary palate, appearing in non-mammalian synapsids and later more fully in the mammalian line, also contributes to this theme by separating airflow from the oral cavity and improving the coordination of chewing and breathing. The Field Museum specifically lists the bony secondary palate among the mammalian features documented by non-mammalian synapsids, showing again that the architecture of survival was not one trait but a package of cooperating innovations. None of this happened all at once, and that is one reason the fossil record matters so much. If evolution only left us the beginning and the end, the transformation would seem absurdly abrupt. Instead, synapsids, therapsids, cynodonts, and early mammalia forms preserve a gradual concentration of the key changes. Reviews of craniodental anatomy in Permian to Jurassic cynodonts explicitly frame this transition as one in which evolutionary changes were concentrated in the cranial and dental region, while studies of the lower jaw revisit the trend toward an enlarged dentary and the eventual mammalian condition. Transitional fossils do not merely show mixture for the sake of mixture. They show function being redistributed. More force here, less bone there, sharper occlusion in one lineage, a stronger new joint in another. It is change by accumulation rather than theatrical reinvention. What is especially striking is how often these innovations appear tied to ordinary biological demands. Better food processing supports more demanding lifestyles. Stronger and more precise jaw mechanics support dietary flexibility. A reorganized ear improves sensitivity to airborne sound. A palate that lets an animal breathe more effectively while using the mouth heavily helps sustain activity. None of these advantages requires grand evolutionary foresight. They only require that, generation after generation, animals with slightly better solutions leave more descendants under real-world conditions. And the real-world conditions of the Permian and Triassic were not gentle. They included harsh climates, ecological competition, and after the end Permian extinction, a recovery world in which only a narrow surviving branch carried the synapsid experiment forward. That context is part of what makes these anatomical shifts feel so consequential. They were not developed in comfort. There is also a useful humility in all this. Humans are often tempted to think of intelligence as the great distinguishing feature of our lineage, and naturally we are very pleased with ourselves about it. But before brains enlarged, before hands became dexterous in the primate sense, before language or tools or long-distance planning, there was the simple but decisive matter of building a better mouth. A lineage that can eat more effectively, fuel itself more consistently, and coordinate its skull structures more efficiently is a lineage buying time and opportunity. The path to large brains does not begin with contemplation. It begins with engineering. Teeth, jaws, and the skull had to become capable first. Paleontology has a slightly cruel way of reminding us that our loftiest achievements rest on very old solutions to very practical problems. So when we say that before dinosaurs something almost became us, this is one of the places where that sentence stops sounding poetic and starts sounding anatomical. The mouth of a later synapsid or cynodont was not a mammalian mouth yet, but it was no longer an ordinary early amniote one either. It was a working draft of the mammalian feeding system, with differentiated teeth, stronger and more coordinated jaw mechanics, an increasingly dominant dentary, and a skull already reorganizing around new priorities. That made these animals better at surviving in their own worlds, and it also left their descendants with a head start in worlds yet to come. Once a lineage begins solving food, force, and sensory function in this integrated way, the rest of the body is likely to follow because a more capable head often demands a more capable metabolism, more reliable airflow, and a more active life to make full use of it. And that is where the story naturally moves next. because once chewing becomes more efficient and the skull begins separating feeding from breathing, it becomes much harder to ignore the larger physiological question. A body with better oral processing and improved airflow is a body edging toward a different energetic style, one less tied to the old rhythms of external conditions and more capable of sustaining itself from within. If teeth and jaws were the visible machinery of the mammal line being rebuilt, then the next layer down was the body itself, and this is where the story becomes slightly more delicate, because people love to divide ancient animals into cold-blooded and warm-blooded, as though nature spent millions of years waiting to hand out one neat badge or the other. It did not. Modern mammals are endotherms, meaning they produce body heat metabolically and regulate body temperature far more independently of outside conditions than typical ectotherms do. But the origin of that condition in our lineage is still debated in detail, and the current evidence points less to a sudden switch than to a stepwise, uneven transition that began somewhere among Permian and Triassic therapsids and continued through later cynodonts and early mammalia forms. Isotopic work, bone histology, skull anatomy, posture, and more recent studies on early mammalia form physiology all point to a mosaic process rather than one dramatic moment when the lights came on and the lineage announced itself fully mammalian. That is important because warm blood is really shorthand for a whole package of changes. It is not just about being pleasantly heated in bad weather. Endothermy in living mammals comes with high and sustained metabolic output, elevated aerobic capacity, better internal temperature control, and a body architecture that can support constant activity without relying so heavily on the kindness of the sun. When paleontologists look for the origins of that package in therapsids and cynodonts, they do not find one clean answer. The 2017 oxygen isotope study on Permo-Triassic therapsids proposed that elevated thermal metabolism appeared independently in at least some dicynodont and cynodont branches, with the mammalian line rooting its version in Echinoodontia during the middle to late Permian. Later review work has argued instead for a stepwise emergence beginning in the late Permian and accelerating in the early Triassic. And then the 2020 Nature Communication study on Morganocodon and Craniotherapsids complicated things further by finding reptile-like basal metabolic rates in these early stem mammals, despite signs of somewhat increased maximum metabolic capacity. That is not a contradiction so much as a reminder that physiology is built in pieces, so the right way to picture this is not as a tidy ladder with cold-blooded synapsid at the bottom and proper mammal at the top. It is more like a body being rewritten in stages, with some systems moving ahead of others. Increased aerobic performance may have come before full mammalian-style basal metabolism. Better breathing mechanics may have appeared before complete thermal independence. Elements associated with insulation or sensory specialization may have evolved while other aspects still looked rather old-fashioned. That mosaic pattern is exactly what the fossil evidence keeps showing. The same recent 2024 paper on Triassic stem mammal skulls notes that the origin of endothermy is usually linked with a whole cluster of mammalian traits, but also emphasizes that many of the classical fossil proxies are indirect and need to be handled carefully. And the 2023 study on maxilloturbinals argued that those structures in living mammals do not map neatly onto thermal biology in the way older assumptions suggested. In other words, the body did not evolve according to one simple checklist, which is probably just as well because nature has never once shown any interest in simplifying a textbook. Even so, some broad changes do stand out very clearly. One of them is the increasing separation of breathing from feeding. Mammals are very good at handling both at once compared with many earlier vertebrates. The bony secondary palate is a major part of that story. In mammals, it separates the nasal passage from the oral cavity, allowing air to continue moving while the mouth is occupied with food. Non-mammalian synapsids document the history of this structure well enough that the Field Museum specifically lists the bony secondary palate among the distinctive mammalian features preserved in the fossil record of synapsids. Reviews of synodont craniodental anatomy describe the secondary palate as a recurring and increasingly important feature through the group, and more recent work on Triassic stem mammal skulls similarly emphasises its posterior expansion and role in restructuring the nasal and oral pathways. That does not mean every animal with a secondary palate was automatically endothermic, because crocodilians also have one, but it does mean the mammal line was becoming better at sustaining airflow while processing food, which is exactly the sort of thing a more active metabolism would appreciate. Once you start thinking about breathing as engineering rather than background scenery, the rest of the body begins to look different too. An animal that wants to maintain high levels of activity cannot afford a respiratory system that works only tolerably when standing still and then starts complaining the moment it moves. Sprawling locomotion in many early tetrapods tends to involve side-to-side bending of the trunk, which can interfere with effective ventilation during sustained movement. Reviews of endothermy in synapsids and archosaurs note that the rise of endothermic physiology likely paralleled shifts away from sprawling gaits, while a 2024 Royal Society paper on vertebral function found that synodonts stabilized the posterior trunk against lateral bending and evolved new axial capabilities compared with earlier non-mammalian synapsids. That does not prove a full mammalian respiratory style by itself, but it does suggest a body increasingly organised around movement and breathing that were less in one another's way. A torso that twists less like a lizard and supports ventilation more effectively is a torso stepping toward a different kind of life. That shift in posture is easy to underappreciate because it sounds like a small matter of leg placement. It is not. Limbs brought more effectively beneath the body can change weight support, stride efficiency, stability, and the relationship between locomotion and respiration. Earlier synapsids still carried plenty of sprawling ancestry in their skeletons, but later therapsids and synodonts increasingly experimented with more upright mechanics. The Field Museum includes upright limbs among the mammalian features documented in non-mammalian synapsids, and recent research on synapsid trunk function suggests that the functional reorganization of the body was happening in stages rather than one abrupt leap. So when we talk about the body being rewritten, we mean exactly that. The change was not confined to the skull. The whole machine was being altered so that a more active head, with better chewing and more efficient feeding, sat atop a body increasingly capable of supporting the energetic consequences. The chest and breathing apparatus are harder to reconstruct directly, which is a polite scientific way of saying that ancient animals did not preserve their soft tissues for our convenience nearly often enough. But paleontologists have still found hints. A 2013 study on the origin of the diaphragm argued that the diaphragmaticus muscle of crocodilians and developmental evidence in mammals may help explain how the mammalian diaphragm was derived evolutionarily, and it specifically notes that Thrinaxodon possessed a suite of traits, including heterodont teeth and a complete secondary palate, that place it within this important transition. Meanwhile, a 2022 paper on the earlier segmental sternum in a Permian synapsid pushed a distinctly mammalian-style sternum deeper into theriodont history than previously recognised. Taken together, these studies do not let us sketch a fully modern mammalian chest onto Permian therapsids, but they do show that the structural underpinnings of mammalian-style breathing were not invented at the last minute. Pieces of the support system were arriving earlier than once assumed. Another clue comes from the nose, though this is also where one has to resist a certain fossil romance. For years, respiratory turbinates or turbinate-like structures were often treated as especially strong evidence of endothermy, because in living mammals and birds the nasal cavity plays an important role in warming, humidifying and conserving heat and water during breathing. That general principle still matters. Nasal passages are not just empty tubes, but recent work has made the picture more careful. The 2024 scientific report study on Triassic stem mammal skulls did not identify ossified turbinals in its sampled taxa and argued that even if non-ossified structures were present, they would not necessarily map directly onto endothermy. Likewise, the 2023 Nature Communications study on mammalian maxilloturbinals found no evidence that their evolution simply reflects thermal biology. So the current view is more restrained. The mammal line was certainly reorganizing the nasal cavity in ways relevant to respiration, moisture handling, and perhaps brain cooling, but no single bony ridge should be forced to carry the whole argument for warm blood on its own. The nose was changing, yes. It was just doing so in the usual evolutionary way, which is to say, with enough complexity to keep specialists employed for decades. What can be said more confidently is that improved airflow, better chewing, and more active locomotion would all have favoured bodies with higher and more sustained aerobic performance. That is one reason researchers often discuss endothermy in terms of different components, especially maximum metabolic rate and basal metabolic rate. The 2020 Morgan-Eucadon study is useful here because it found evidence suggesting that maximum metabolic rates may have increased before basal rates reached the level seen in living mammals. In simpler terms, the lineage may have become better at bursts or sustained activity before it became fully mammalian in the everyday energy cost of simply being alive. This is a very sensible evolutionary possibility. A body can be pushed first toward doing more before it is pushed toward paying the full internal heating bill all day long. That may sound slightly unfair from the body's perspective, but it is an entirely familiar pattern in evolution. One system advances, the others catch up later, and somewhere in the middle paleontologists have to explain why the result looks like three answers at once. Growth patterns add another layer. Bone histology in various therapsids and synodonts has revealed fibrolamellar bone and other signs associated with rapid growth in some taxa, and this has often been discussed as evidence for elevated metabolic activity. The oxygen isotope study itself summarizes earlier bone histology work showing that several therapsid groups display such tissue, while the broader 2021 review on Synapsid and archosaur endothermy ties bone histology into a picture of stepwise physiological change across the Permian-Triassic transition. None of this means every therapsid was a mammal in physiological disguise. Far from it. But it does suggest that faster growth and more sustained metabolic investment were appearing in important parts of the lineage. A body growing quickly, moving more effectively and handling oxygen better is not yet a modern mammal, but it is clearly being asked to do more than a typical sprawling ectotherm. The timing of all this is especially interesting because it overlaps with environmental crisis. The isotope paper proposed that major climatic and environmental fluctuations were likely selective pressures favouring elevated thermal metabolism in certain therapsid groups. The Benton review goes further and explicitly links the stepwise emergence of endothermy to the upheavals surrounding the end Permian mass extinction and early Triassic world. That does not mean disaster automatically creates warm blood, which would be a very tiresome rule if it were true, but it does suggest that animals capable of sustaining activity, buffering their internal state, and operating across wider external conditions may have had advantages in unstable environments. If the world becomes hotter, drier, more seasonal, less predictable, and ecologically disordered, a lineage that can depend a bit less on perfect outside conditions may fare better. Not always, of course. Evolution never guarantees a reward for effort, but in a shaken world, physiological flexibility can become more valuable very quickly. This is also where the story becomes more human than it first appears. Mammals are, by and large, animals that carry a great deal of their environment inside themselves. We regulate heat. We ventilate continuously and efficiently. We process food thoroughly. We sustain long periods of activity. We maintain expensive tissues, including very demanding nervous systems, by running a high metabolic budget. None of that began with humans, primates, or even with true mammals. It began with older lineages gradually uncoupling themselves from immediate environmental limits. Therapsids and synodonts were not yet living the full mammalian physiological package, but they were rewriting the terms on which the body operated. They were reducing dependence on one mode of life and inching toward another. That is part of why the secondary palate, the more stable trunk, the changing sternum, and the gradual increase in metabolic performance all belong in the same story. They are different parts of the same practical problem: how to build an animal that can keep going. There is also a useful caution in all this, which is that not every classic mammalian trait should be read as direct proof of full mammalian physiology. A secondary palate alone does not settle the matter. Nasal structures do not offer a universal thermometer. Even an early mammalia form may still retain reptile-like features in important metabolic respects. That is why the recent literature has become more careful and, in a way, more satisfying. Instead of asking for the exact moment mammals became warm-blooded as if nature were waiting to stamp a certificate, researchers increasingly describe a stepwise assembly of mammalian biology. Some traits appear early, others follow later. Some evolve in parallel in different groups, others are lost or modified. The result is less tidy but far more believable. Bodies are not transformed by slogans. They are transformed by the accumulation of workable changes, each useful enough to stay. So when we say the body was rewritten, that is not exaggeration. The mammal line was changing how it breathed, how it moved, how it grew, how it handled heat, and how it balanced the demands of feeding and activity. The evidence does not point to a single clean threshold, but to a long and difficult upgrade, one that likely began in late Permian therapsids, accelerated in Triassic cynodonts, and still was not fully complete even in some of the earliest mammalia forms. That is a wonderfully ancient kind of progress. Not quick, not neat, but stubborn. And once the body is being rewritten that thoroughly, the next step almost announces itself, because some of the bones that once helped this lineage bite and breathe were about to begin another career altogether, trading the work of the jaw for the finer business of hearing. And that is where the next change begins to sound almost impossible, because it asks us to picture an animal using part of its jaw to hear the world. Not in the poetic sense, not as a metaphor, but literally. In early synapsids, as in most other non-mammalian tetrapods, the jaw joint was formed by two bones called the quadrate and the articular. Mammals do things differently. Our functional jaw joint is between the dentary and the squamosal, and our middle ear contains three tiny ossicles instead of the more typical single-bone condition seen in other living terrestrial vertebrates. The extraordinary part is that these two facts are connected. The quadrate and articular of ancestral synapsids did not simply disappear. Over evolutionary time, they were transformed into the incus and malleus of the mammalian middle ear, while the jaw itself adopted a new articulation. In other words, part of the old feeding machinery was reassigned to sound. This is one of those evolutionary stories that seems almost too neat to be true, which is probably why it took a long time for people to accept it fully. But the evidence from comparative anatomy, embryology, and fossils has become one of the clearest examples of large-scale anatomical repurposing in vertebrate history. Reviews of mammalian jaw and ear evolution describe the three-ossicle middle ear and the novel mammalian jaw joint as evolving together, not as separate inventions. UC Berkeley's evolutionary overview puts it plainly. Early synapsids had a quadrate articular jaw joint. Several later synapsid lineages evolved a second jaw articulation alongside it, and eventually the quadrate and articular shrank, shifted into the ear region, and became the anvil and hammer. That is not just a change in what a bone is called, it is a change in what a bone is for. It helps to begin with the ancestral setup. In the earliest synapsids, the lower jaw was not the single dentary bone that mammals have now. It was a more crowded arrangement, built from multiple bones, with the articular at the back of the lower jaw meeting the quadrate at the rear of the upper jaw to make the joint. The teeth sat mainly in the dentary, but the full act of biting still depended on this older architecture. At the same time, hearing in these animals did not yet involve a mammalian chain of three ossicles. Non-mammalian cynodonts and more basal synapsids are understood to have had a middle ear arrangement very different from the triossicular mammalian ear, and more comparable, in broad terms, to the single-bone sound transmission system of other non-mammalian amniotes. So at the start of the story, chewing and hearing are not yet cleanly separated jobs. They are still sharing structural real estate. That sharing matters because a bone cannot be equally excellent at two very different careers at once. A jaw joint bone must help bear load, transfer force, and survive the stress of biting. An ear ossicle must be small, mobile, and well suited to transmitting vibrations. Those are not compatible ambitions. The old arrangement worked well enough for early synapsids because evolution is under no obligation to optimize everything at the same time. But once the dentary began to enlarge and the musculature of the jaw began changing, the possibility opened for a different division of labour. Reviews of lower jaw evolution show a long-term trend toward enlargement of the dentary relative to the rest of the jaw, while studies of cranial function describe a broader reorganisation of the skull, marked by bone reduction, a new jaw joint and changed muscle arrangements. In practical terms, the front of the lower jaw was taking on more authority, which meant the old rear elements could gradually become less load-bearing. For a time, the lineage seems to have lived with both systems at once. Berkeley's Synapsid evogram describes transitional forms such as probenognathus, in which a second jaw articulation involving the dentary and squamosal evolved alongside the older quadrate articular one. That double-jointed phase is one of the most satisfying parts of the whole story, because it gives us a mechanically plausible bridge rather than a sudden leap. The new joint did not appear only after the old one vanished. For a while, both were present. The dentary squamosal articulation could begin taking over the work of biting while the ancestral elements persisted nearby. It is rather like renovating a bridge while traffic still has to cross it every day, except the engineers are natural selection and geological time, which means the project takes millions of years and nobody wears a hard hat. Once the new joint became more functionally important, the old one was free to change in a way it never could have while still doing the heavy work of chewing. Berkeley's summary explains that the quadrate and articular lost their role in jaw articulation, became smaller, and shifted toward the ear region. Reviews of mammalian ear evolution trace the same transformation in more technical language, identifying the quadrate as the precursor of the incus and the articular as the precursor of the malleus. The angular bone of the lower jaw also contributed to the mammalian ear region, becoming the ectotympanic, the bony support for the eardrum, so the mammalian ear was not built from entirely new parts, it was built by redeploying old ones. The jaw was not stripped and replaced, it was edited. This is one reason the evolution of the mammalian ear is often used as a textbook example of exaptation, where an existing structure is co-opted for a new role. The old post-dentary bones were first parts of a feeding mechanism, then transitional elements in a changing jaw, and eventually key parts of a sound-transmitting apparatus. Berkeley explicitly frames the pattern that way, noting that the arrival of the dentary squamosal jaw joint allowed the quadrate and articular to acquire a completely different function. That functional shift was likely not driven by one single cause. Berkeley also notes that researchers have suggested improved hearing, increasing brain size, or both as possible factors, and that these ideas are not mutually exclusive. Evolution rarely acts for only one reason anyway. It is usually happier to take one workable change and make it useful in several ways at once. There is also something deeply practical about why a small earbone chain would matter. Mammals hear airborne sound with unusual sensitivity, especially at higher frequencies, in part because the malleus, incus, and stapes form a tiny lever system that transmits vibrations efficiently from the eardrum to the inner ear. The modern mammalian middle ear is one of the defining osteological traits of the class, precisely because it is so distinctive. The old jawbone system was never going to provide that level of auditory delicacy while still serving as a chewing hinge. Once those bones became smaller and less burdened by feeding forces, they could specialise. The result was not merely better hearing in some vague sense, but a radically different auditory design. The same anatomical region that had once helped hold the jaw together was now involved in detecting much finer sound. Of course, this did not happen in one quick, orderly line. One of the most useful lessons from fossil mammals and mammalia forms is that the separation of ear from jaw passed through intermediate stages that were both real and anatomically awkward in exactly the right way. Research on transitional mammalian middle ears has identified forms in which the hearing bones were decoupled from direct jaw function, but still connected to the mandible through ossified Meckel's cartilage. The 2011 description of Leoconodon highlighted precisely this sort of arrangement, a middle ear detached from the lower jaw in the expected way, yet still held in place by an ossified cartilage resting in a groove on the jaw. More recent work on mammalian development and fossil transitions describes a two-step pattern, with a partial or transitional middle ear first, followed later by breakdown of Meckel's cartilage and the fully detached definitive mammalian middle ear seen in living mammals. That transitional stage is especially appealing because it solves a common intuitive objection. People often hear that jaw bones became ear bones and imagine a sort of impossible jump, as though a working jaw simply misplaced several parts one morning and hoped for the best. But the fossil and developmental evidence say otherwise. There were stages in which the bones had shifted functionally but remained connected, stages in which the new jaw joint had taken over, but the old elements were not yet fully free, and stages in which the final disconnection happened later. Development in living mammals still reflects this deep history to a limited degree, since the ossicles arise from embryonic structures homologous to the ancestral jaw elements, and only later assume their definitive adult relationship. The past lingers in development because anatomy has a very long memory. The story also turned out to be more tangled than earlier paleontologists hoped. It would be comforting if there were one clean march from jaw to ear, and every lineage followed it obediently. But several studies have shown that the evolution of the mammalian middle ear involved convergence and repeated modification in different mammalian groups. The 2016 phylogenetic analysis on middle ear evolution concluded that full detachment of the middle ear bones from the post-dentary trough occurred only twice among mammals, once in the ancestors of therians and once in monotrims. Other studies of Mesozoic mammals similarly argue that some ear bone features evolved independently in different lineages. So even here, in one of the best-known examples of major transformation, evolution still refused to proceed as a single straight ladder. It found related solutions more than once, which is both scientifically interesting and mildly irritating if you were hoping for a tidier diagram. That complexity does not weaken the larger point. If anything, it strengthens it. The broad transformation is secure. The quadrate and articular correspond to the incus and malleus. The mammalian jaw joint is new relative to the ancestral amniote one, and the two systems evolved together. What varied was the exact route by which different mammalian lineages achieved the final detached middle ear condition, and that is entirely in keeping with the larger synapsid story. Mammalian traits were assembled gradually, in mosaics, across multiple lineages, with some features appearing early, some late, and some more than once. The jaw-to-ear transition is not a magic trick. It is a prolonged and well-documented redistribution of function. There is also a subtler consequence of this transformation, and it brings us back to the broader logic of mammalian survival. By moving the old jaw elements out of the business of bearing bite force, the lineage did not just improve hearing. It also made the jaw itself more specialized for chewing. The emergence of the dentary-scomosal joint is tightly tied to stronger and more precise feeding mechanics, while the shrinking post-dentary bones could be spared for auditory refinement. This is why studies of cranial reorganization treat jaw function, muscle arrangement, and middle ear evolution as one integrated event rather than separate stories. Feeding and hearing, far from competing forever, were gradually disentangled so that both could become better. Mammals inherited the outcome, an efficient chewing apparatus and a sensitive middle ear, both built from a single ancestral complex that had been sorted into new roles. And it is hard not to admire the sheer practical cleverness of that result, even though cleverness is the wrong word for a process with no foresight. ancient synapsids did not set out to improve high-frequency hearing. They were simply changing their jaws, their muscles, their skull proportions, and eventually their lifestyles in ways that made some old structures less necessary for biting and more available for something else. But once tiny bones begin transmitting sound instead of bracing a jaw, the acoustic world opens up differently. Later mammalian hearing would become particularly good at detecting small, high-frequency noises, a useful trait for animals living active, often nocturnal lives among insects and other small prey. The jawbones were not trying to become ear bones. They were becoming dispensable to one job and therefore recruitable for another. That is how evolution often does its best work, not by inventing from nothing, but by freeing something old to do something new. So when jawbones began learning to hear, the change was not mystical or symbolic. It was mechanical, gradual, and astonishingly consequential. A lineage that had already rebuilt its teeth, strengthened its dentary, and reorganized its breathing and posture was now also rewriting the architecture of the side of the head. The old quadrate articular joint gave way to the dentary squamosal one. The articular and quadrate became the malleus and incus. The angular contributed to the eardrum supporting ring. Transitional animals carried ears still tethered to the jaw by cartilage, before later mammals completed the separation. And by the time the process had run far enough, the mammalian head had become something genuinely new, a structure that could bite with one set of parts and listen with another. That was a remarkable achievement for a lineage that still had not yet become fully mammalian in every other respect. And it would matter even more because this slow, careful redesign was happening in a world that was about to suffer a catastrophe so large that almost all of it could have been erased before the new arrangement had much chance to prove itself. For all the careful changes that had been accumulating in the synapsid line, the stronger jaws, the better teeth, the reshaped skull, the hints of a more active body, none of it came with any promise of safety. Evolution does not protect a lineage because it has been interesting, or because it happens to be building something that will matter later. Around 252 million years ago, at the Permian Triassic boundary, Earth passed through the most severe mass extinction event known in the Phanerozoic. Calling it a single day is only a human shortcut. In geological terms, the main crisis may have unfolded over something like 60,000 years, perhaps a little more, perhaps a little less, which is still shockingly abrupt for a global biological collapse. The scale of the loss is hard to hold in the mind for very long without it turning into a statistic and losing its force. Marine ecosystems were devastated, with studies and reviews commonly placing marine species loss above 80%, and in some estimates closer to 90 or more. On land, the disaster was severe enough that one recent Nature communication summary described roughly 70% loss among land vertebrate families, and another recent review called it the most severe terrestrial ecological crisis in Earth's history. It was also the only mass extinction known to have struck insects at that scale. This was not a regional crash, not a difficult period for a few unlucky groups, but a planetary failure of living systems across sea and land alike. The leading cause, and now the dominant explanation, is the Siberian traps, one of the largest volcanic outpourings in Earth history. These eruptions were not a single neat event, but an immense episode of large igneous province volcanism in what is now Siberia. Work on the timing of the extinction and magmatism has shown that a key pulse of sill emplacement was closely aligned with the crisis itself, and later studies have reinforced the link between Siberian traps activity and the environmental collapse. In simple terms, the planet was hit with a prolonged and deeply disruptive volcanic assault, and some of the most damaging phases arrived at exactly the wrong time for everything else alive. What those eruptions did was not limited to lava pouring across the landscape, though that would have been dramatic enough from a safe and very distant vantage point. The more important effects came through the atmosphere, the oceans, and the chemical systems that keep the planet broadly livable. The Siberian traps released very large amounts of volcanic gases, including carbon dioxide and sulfur dioxide, and the knock-on effects likely included intense warming, acid rain, ozone damage, wildfire activity, toxic metal release, ocean acidification, and severe oxygen loss in marine environments. 120.23. Nature Communication Study described centennial-scale pulses of environmental deterioration and recurrent wildfires around the onset of the extinction. Another 2024 Nature Communications paper emphasized repeated volcanic pulses and linked them to catastrophic environmental changes across both marine and continental settings. Temperature appears to have been one of the central drivers of the disaster. A 2021 analysis of temperature thresholds for mass extinctions estimated that the end Permian event occurred during warming greater than 10 degrees Celsius, which is not the sort of climatic inconvenience most ecosystems can absorb and carry on with. In the oceans, warming also reduced oxygen availability and worsened hypoxic stress. A 2018 science study argued that temperature-dependent hypoxia can explain much of the biogeography and severity of the marine extinction, which is an efficient way of saying that many marine animals were pushed into water that had become too hot and too oxygen-poor for them to survive. It is difficult to overstate how destructive that combination would have been. Heat alone is bad enough. Heat plus suffocation is far worse. Marine collapse is often the part of the story that gets the most attention, partly because the fossil record at places like Meishan in South China preserves it with unusual clarity. But the land did not escape. Forest systems were badly disrupted, wildfire signals increased, plant communities were hammered, and the food webs built on them were shaken loose. The ancient terrestrial world did not simply lose a few dominant animals and then continue in reduced spirits. It was reorganized from the ground up. A recent study on environmental deterioration before the extinction points to repeated wildfire pulses in the terrestrial realm, and the 2024 paper on the terrestrial crisis in northwest China stresses that the event on land was itself a major ecological catastrophe, not just an aftershock from the sea. Even the timing on land may have been more complicated than people once thought. For a long time, the marine and terrestrial extinctions were often treated as if they happened in lockstep everywhere. But a 2024 Science Advances study argued that, in the Paleotropics, the terrestrial end Permian mass extinction post-dated the onset of the main marine event. That does not make the crisis any gentler. If anything, it makes it more unsettling, because it suggests the collapse rolled through different environments with some degree of mismatch and lag, rather than as one perfectly synchronized blow. Life on land may have watched the planet coming apart before its own systems finally failed. That is not especially comforting, though I suppose it is geologically interesting. For the Synapsid line, this was the moment when all the earlier experimentation came closest to meaning nothing. Before the extinction, therapsids had been diverse and important across terrestrial ecosystems. They included large herbivores, major predators, and several branches in which distinctly mammalian traits were becoming more pronounced. After the extinction, that diversity was cut down brutally. Entire parts of the therapsid world disappeared. What survived was not the old breadth of the lineage, but a much narrower remnant. If you were to compare the late Permian synapsid world with the immediate post-extinction one, the difference would not look like ordinary turnover. It would look like the difference between a forest and its charred edge. Among the therapsids that did make it through, Dicynodonts were especially important, and within them Lystrosaurus became the most famous survivor of all. It was one of the few tetrapods to cross the extinction boundary and then become extraordinarily abundant in the early Triassic. Multiple studies on Lystrosaurus describe it as a survivor of the end Permian event and note its remarkable dominance in the harsh world that followed. If you had walked through some early Triassic landscapes, the odds of meeting a Lystrosaurus would have been uncomfortably good. It was not a glamorous animal by modern standards. It looked a little like an overbuilt, tusked, beaked experiment in practical herbivory. But the post-extinction world was not handing out prizes for elegance. It rewarded whatever could persist. The other surviving branches mattered too. Therocephalians, which had already been a diverse therapsid group in the Permian, survived the extinction in several genera and remained significant parts of Triassic recovery faunas in the Karoo Basin. Huttenlocher's work on Therocephalians highlights genera that cross the boundary and emphasises how useful the clade is for studying post-extinction body size reduction and recovery. Cynodonts also made it through, and that matters enormously for our story because cynodont therapsids later diversified extensively after the Permo-Triassic crisis and eventually gave rise to mammals. So although the synapsid line was slashed back, it was not completely erased. The branch that mattered most to us survived, but only just, and not with anything like its former variety intact. The animals that survived were not simply the same creatures carrying on as before. The aftermath imposed its own rules. One recurring pattern after mass extinctions is a reduction in body size, often called the Lilliput effect, and therapsid survivors appear to show it as well. Huttenlocher's work on Therocephalians discusses post-extinction body size reductions explicitly, and the broader picture of early Triassic tetrapods is one of compressed, stressed faunas living in a world that had become ecologically simpler and physically harsher. Large-body dominance was not the order of the moment. Survival favoured smaller, faster maturing, more flexible forms. Deep time, when under pressure, becomes surprisingly unsentimental about grandeur. Lystrosaurus again is a good example of how survival may have depended on a whole package of practical traits. Studies of its growth and life history suggest early Triassic individuals reached maturity quickly and likely had shortened life expectancies compared with some Permian relatives. A 2016 study argued that breeding younger may have been an important survival strategy in the unstable post-extinction environment. Another isotopic study suggested that the therapsid clade surviving the crisis may have benefited from elevated thermometabolic capabilities, helping them cope with the climatic volatility around the boundary. None of this means Lystrosaurus was some perfect evolutionary champion. It means that in a devastated world, animals that could grow fast, reproduce sooner, and keep functioning under extreme conditions had a better chance than those built for calmer ages. The post-extinction world itself was miserable for quite a while. Recovery was not instant, and in many places it was not especially orderly. Reviews of early Triassic terrestrial faunas emphasize a prolonged interval of low diversity and ecological simplification, and work on delayed tetrapod recovery notes that diversity remained depressed through much of the early Triassic. Plant communities were patchy and often dominated by opportunistic forms in disturbed settings. Animal communities were less diverse and more uneven than before. It was not simply that life had survived, it was that life had survived into a world still not properly fit for comfort. Anyone hoping for a swift return to normal would have needed geological patience. This is part of why the extinction matters so much to the mammal story. It was not merely a dramatic background event that happened to precede later success. It was a bottleneck that stripped the synapsid line down to a few surviving branches and forced the future of mammals through a narrow opening. Before the extinction, the lineage had many forms and many possible directions. After it, the line leading toward mammals continued, but in reduced company. The great pre-dinosaur experiment in synapsid life did not carry forward in all its breadth. It carried forward through a handful of survivors and their descendants. What would later become mammals was not the untouched continuation of a flourishing Permian world. It was the salvage line. There is something sobering about that, because it means our own existence depends not only on the slow invention of mammalian traits, but on those traits or the broader bodies carrying them getting through the worst ecological disaster in the history of complex animal life. If the relevant cynodont lineages had failed, or if the surviving therapsids had been only those branches that later led nowhere near mammals, the whole later story disappears. No true mammals. No mammalian radiation after the dinosaurs. No primates. No us. The phrase "something almost became us" becomes very literal here. The almost is the end Permian extinction. It is the point where the line very nearly stops, and yet it did not stop. That is the crucial part. The synapsid world was broken, but not finished. Lystrosaurus and a few other survivor lineages moved into the emptied landscapes of the early Triassic. Therapsids persisted for a while. Cynodonts, though initially modest, went on diversifying in the aftermath. The old Permian dominance of broad therapsid faunas was gone, but the small surviving branch that matters most to us was still there, making its way through heat, instability, low diversity, and the long aftermath of planetary crisis. It would not rule the next age. That privilege would increasingly belong to Archosaurian lineages. But survival is sometimes more important than dominance, and in this case survival was enough. So the day the Permian world almost ended was not the end of our story. It was the point at which the story became fragile. The mammal line had been shaped for millions of years before dinosaurs ever appeared, and then it was nearly erased before dinosaurs had their chance to rise. What came through the extinction was not a triumphant procession, but a reduced, stressed, stubborn remnant, and that remnant matters more than all the vanished abundance around it, because from those few surviving branches came the cynodont descendants that would eventually produce true mammals, small enough and resilient enough to persist through the long age that followed, when the world above them would increasingly belong to something else. What came through the end Permian disaster was not a triumphant new ruling class. It was a reduced and rather vulnerable branch of the old Synapsid lineage, and for a very long time its descendants did not dominate the land at all. The Triassic and the periods that followed increasingly belonged to archosaurs and then to dinosaurs, while the mammal line persisted in smaller forms, often in niches that did not invite much attention from giant daytime reptiles. This is where the story can be easy to oversimplify. It is true that mammals remained small for most of the age of dinosaurs. It is also true that they spent a very long time living in the literal and ecological shadow of much larger animals. But it is not quite right to imagine them as passive little extras, all identical, all shrew-like, all doing the same nervous scurry for 150 million years. The fossil record now shows something much richer than that. Mammalia forms appear by the late Triassic, with groups such as harameids, morganocodonts, and queniotheriids already distinct from one another in dental form and chewing function, which means the line was diversifying early even before true mammals become clearer in the record. That distinction between mammalia forms and crown mammals is worth handling carefully, because the naming can become a small geological swamp if left unattended. Mammalia forms includes true mammals, and some very close extinct relatives that had already acquired many mammalian traits, but may fall just outside the crown group. By the late Triassic and early Jurassic, forms such as Morganocodon were already present in Europe, China and North America, and they show many of the classic features associated with the mammalian line, even if some aspects of their biology remained more primitive than those of later mammals. That is why paleontologists sometimes speak of the mammalian way of life, emerging in stages, with the earliest mammalia forms already carrying much of the anatomical toolkit, while physiology and ecology continue to evolve afterward. The important practical point is that by the time dinosaurs were rising, the mammal line had already crossed into recognisably mammalian territory, even if it had not yet become anything remotely dominant. For most of the Mesozoic, body size remained modest. Communications biology notes that Mesozoic mammals were once thought to have been restricted to sizes below about 5 kilograms, and while later discoveries have complicated that picture, the basic impression still holds. Most were small animals. A few forms broke the stereotype, most famously Repenomamus giganticus, which reached something like 12 to 14 kilograms, but such cases were exceptions rather than the rule. In general, early mammals and mammalia forms lived at scales more like mice, rats, shrews, voles, squirrels, or small mustelids than anything approaching large modern herbivores or carnivores. This was not because the lineage lacked all ambition. It was because large-bodied terrestrial niches were already crowded with dinosaurs and other reptiles whose dominance shaped the ecological space available. Small size in that context was not just a limitation, it was also a strategy. Small animals can hide, burrow, mature more quickly, exploit patchy food, and survive in microhabitats that giants cannot use. That helps explain why the old image of early mammals as tiny survivors underfoot is partly right and partly misleading. They were underfoot, certainly enough. If you stood in a Jurassic forest while a large dinosaur passed through, a mammal would have seemed an afterthought by comparison. But the small-bodied world is not a minor world. It is full of burrows, roots, leaf litter, insects, eggs, seeds, carrion scraps, small vertebrates, bark crevices, stream margins, and nighttime opportunities. To an animal the size of Morganocodon or a small docodont, the forest floor was not a neglected margin of the ecosystem. It was an entire continent of smell and texture. The fact that dinosaurs occupied the large, visible, often daytime roles did not leave mammals with nothing. It left them with the sort of ecological detail that rewards agility, hearing, smell and persistence, and those were exactly the kinds of traits the mammal line had been assembling for a very long time. One of the most enduring ideas about Mesozoic mammals is the nocturnal bottleneck hypothesis, the proposal that early mammals were largely or exclusively nocturnal for a very long span of their history, because daytime activity was effectively occupied by dinosaurs and other reptilian competitors. A major review in Proceedings of the Royal Society argues that the hypothesis is ecologically plausible and links it to several mammalian features, while later work on mammalian activity patterns and vision has continued to support a deep nocturnal ancestry for the group. Nature's coverage of the topic summarises the broad conclusion plainly. Early mammals were creatures of the night, and the shift toward broader daytime activity came later, after the non-avian dinosaurs disappeared. This idea should not be treated as a rigid law applying to every lineage at every moment, but as a powerful long-term pattern. Mammals were shaped in darkness for a very long time. That nocturnal emphasis fits remarkably well with the anatomy we have already been tracing. If your lineage evolves better hearing, a stronger sense of smell, more effective heat generation, fur for insulation, and a feeding system capable of supporting active metabolism, nighttime becomes much less forbidding. Darkness is not empty. It is simply a different competitive arena. Dinosaurs, for all their success, were not uniformly adapted to every small nocturnal niche. By working at smaller scales and often after dusk, early mammals could reduce direct competition and avoid many large visual predators. Modern mammals still carry the marks of that history in their sensory systems and activity patterns. The night was not only a refuge, it was a training ground. The small survivors beneath the dinosaurs were not merely hiding there, they were being shaped there. For many years, paleontologists assumed that these early mammals were ecologically conservative as well as small, meaning mostly generalized insect eaters, with minor variations on the same theme. That view has changed dramatically. Communications biology states that fossils of complete skeletons now reveal a diversity of locomotor lifestyles, including swimming, gliding, fossorial, and arboreal forms, while craniodental evidence points to a corresponding diversity of diets. A 2015 Current Biology paper found elevated rates of morphological evolution prior to the late Jurassic, with a pronounced peak during the early to middle Jurassic, supporting a mid-Jurassic adaptive radiation in mammals. In other words, mammals were not simply waiting for the dinosaur extinction to begin experimenting. Much of the experimentation was already underway during the dinosaur era itself. Some of the fossils responsible for this change in view are so striking that they sound almost designed to embarrass older textbooks. Castor accorda, from the Middle Jurassic, was a semi-aquatic mammalia form with a broad, flattened tail and adaptations comparable in function, though not close relationship, to modern swimming mammals. The original description emphasized that early mammalia forms had already developed diverse locomotor and feeding adaptations and were more ecomorphologically varied than the old stereotype of generalized insectivores allowed. Velaticotherium and later forms such as Myopatagium show that gliding evolved early in the mammal line as well, with skin membranes stretched between the limbs for rossarial movement through forest canopies. A Nature feature from 2019 described Jurassic gliders as evidence that this style of locomotion had appeared by about 160 million years ago. That is not the behaviour of a lineage merely marked in time until a lucky asteroid. There were diggers too. The fossil record includes forms interpreted as fossorial or semi-fossorial, and the broader forelimb and postcranial evidence suggests that small Mesozoic mammalia forms were already spreading across multiple locomotor modes. Some were ground dwellers, some climbers, some swimmers, some burrowers, and some gliders. This matters because locomotion is tightly tied to ecology. A burrower uses shelter, temperature buffering, and subterranean prey differently from an arboreal climber. A glider exploits canopy routes unavailable to a digging mammal. A swimmer reaches food and safety in places terrestrial predators may ignore. Once these modes evolve, the small body story stops looking narrow. It becomes a story of many finely partitioned ways to survive beneath a world run by giants. Diet tells the same story. The late Triassic mammalia form Haramiavia already shows that the earliest mammalia forms were not all using the same kind of teeth for the same kind of food. The proceedings of the National Academy paper on Haramiavia states that haramids, Morganucodonts, and Queniotheriids were the three earliest mammalia form groups, and were distinctive from one another in dental morphology and masticatory function. It also notes that haramiids had multi-cusped, multi-row teeth suited to omnivorous or herbivorous feeding, while contemporary Morganucodonts and Cynoconodon had more insectivorous dentitions. Later work on jaw shape and mechanical advantage in Mesozoic mammals similarly concludes that these animals were more ecologically diverse than once assumed. So even while remaining small, they were already dividing food resources in ways that reduced direct overlap and expanded their options. And then there is Repenomamus, which is the sort of fossil that always improves a conversation. Repenomamus robustus from the early Cretaceous was not only unusually large for a Mesozoic mammal, around badger size, but a famous specimen preserved the bones of a juvenile Psittacosaurus in its stomach region. Nature's 2019 feature summarised it bluntly. This species challenges the stereotype of early mammals as diminutive insect-eating fluffballs. The point is not that mammals were suddenly taking over the food chain. They were not. Dinosaurs still ruled the large-bodied terrestrial world, but the existence of a mammal certainly known to have eaten a baby dinosaur is a useful corrective to the old image of mammals as purely timid underclass citizens of the Mesozoic. Some were prey, naturally. Some were probably frequent prey. But some were also active predators taking opportunities when they could. Even in physiology, the picture is subtler than modern mammal, just smaller. A 2020 Nature Communication study on Morganucodon and Queniotherium found evidence that these early Jurassic stem mammals had basal metabolic rates closer to modern reptiles than to living mammals, even while another proxy suggested maximum metabolic rates that were somewhat more mammal-like. The implication is not that they were fake mammals. It is that mammalian physiology, like mammalian anatomy, assembled in steps. Small Mesozoic mammals had many key mammalian traits, but not always the full package at modern levels. They were still in the middle of a long-fused transition. That should not make them seem lesser. If anything, it makes their success under dinosaur-dominated conditions more impressive. They did not need to be modern in every detail to survive brilliantly at small scales. Growth patterns tell a similar story. A 2024 study on Jurassic mammalian growth found that the fossils examined showed slower growth rates, longer lifespans, and delayed sexual maturity relative to comparably sized living mammals. That suggests the life histories of early mammalia forms and crown mammals were not simply scaled-down versions of modern mice or shrews. Some aspects of their biology remained more archaic, even while their skulls, ears, and ecological specializations pushed forward. Again, the broad theme is mosaic evolution. During the dinosaur era, the mammal line was already recognizably itself, but still becoming itself as well. That kind of in-between state lasted an astonishingly long time, and yet within that long interval, real diversification happened. The 2015 current biology analysis found that rates of morphological evolution were significantly elevated prior to the late Jurassic, and that a burst of phenotypic innovation coincided with rising diversity and maximum disparity. Later in the Mesozoic, the pace slowed, but by then the group had already explored a surprisingly wide range of forms. The importance of that result is difficult to overstate. It means the age of dinosaurs was not merely a holding pattern for mammals, it was a formative 2/3 of mammalian history. Communications biology notes that roughly 127 million years, about 65% of mammalian evolutionary history, took place in the Mesozoic. The small survivors were not filling time. They were becoming a versatile lineage in real ecosystems over a very long span. Still, they remained limited in one obvious respect: size. Dinosaurs occupied the great visible spaces of the land, especially by day, and mammals mostly did not contest them there. The result was a world in which mammals became specialists in the kinds of niches that reward refinement rather than bulk. Good hearing matters more in leaf litter than in a sauropod herd. Sensitive whiskers matter in burrows and darkness. Strong teeth for crushing insects, cracking seeds, slicing flesh, or grinding plant matter matter enormously when every calorie counts. Small limbs adapted for climbing or digging can open entire habitats inaccessible to larger bodies. From one angle, the dinosaurs constrained mammals. From another, they forced them to become excellent at details. The big world above belonged to reptilian giants. The intricate world below became mammalian territory. That deep Mesozoic experience may also explain why so many quintessential mammalian traits feel tuned to a life of caution and precision. Fur helps when nights are cold. Endothermy helps when activity cannot wait for sunlight. Acute hearing helps when danger can arrive from overhead. A reliance on smell helps when visibility is poor. Burrowing, climbing, and rapid reproduction all suit a small animal in a world where being noticed is often a very bad development. These traits were useful long before mammals became large and conspicuous. In fact, they were probably built for the exact opposite sort of existence. The power of mammals later, in the Cenozoic, came partly from traits forged when they were not powerful at all. There is an irony in that. The age of dinosaurs is often told as though mammals were waiting for permission to matter. But mammals mattered to themselves the whole time. They were evolving, diversifying, partitioning diets, refining locomotion, and solving problems at small scales with extraordinary persistence. They did not need to displace dinosaurs to become successful on their own terms. They needed only to survive, to keep diversifying without overreaching, and to carry forward the ancient synapsid inheritance that had already passed through the Permian bottleneck. When the dinosaurs finally disappeared at the end of the Cretaceous, mammals did not begin from nothing. They expanded from a long-prepared base. The world after the asteroid did not invent mammalian possibility, it released it. So the tiny survivors beneath the dinosaurs were not a footnote. They were the continuity of a much older story. They were what remained of a lineage that had begun before dinosaurs existed, had nearly been destroyed at the end of the Permian, and then spent the next 150 million years becoming more capable in quiet ways. Small bodies, nighttime habits, burrows, branches, streams, leaf litter, complex teeth, increasingly sensitive ears, and specialized jaws. That was the long apprenticeship of mammals. They stayed mostly small, not because they had no history behind them, but because the history behind them had taught them how to endure in the margins. And in the end, endurance turned out to matter more than grandeur. By the time the age of dinosaurs closed, The lineage that would one day include primates and humans was still physically modest, but it was carrying an inheritance so deep and so thoroughly tested that the final question is no longer whether our story began before dinosaurs. It is whether we are willing to admit how much of ourselves was already decided there. And when you put all of that together, the argument becomes much harder to ignore. Humans are not really a story that begins after the dinosaurs. We're not even, in the deeper sense, a story that begins with the first true mammals. We are the distant outcome of a much older branch of life, one that split away early from the lineage leading to reptiles, dinosaurs and birds, and then spent the Permian building many of the structures that later made mammals possible. The fossil record of non-mammalian synapsids preserves the history of a bony secondary palate, complex tooth occlusion, upright limbs, and the incorporation of lower jaw bones into the middle ear, and modern mammals are the only surviving synapsids left. That means the deeper roots of our own anatomy sit in a lineage that was already becoming distinct long before the first dinosaur existed. That is the first correction this story asks us to make. The popular version goes something like this: dinosaurs vanish, mammals get their chance, and after enough time, one branch eventually produces us. There is some truth in that, but it places the beginning far too late. By the time mammals were living beneath the dinosaurs, the hard anatomical work had already been underway for tens of millions of years. The jaw had been reorganizing, the teeth had been differentiating, the palate had been changing, and the old jaw bones had begun the long transition toward the mammalian middle ear. Those are not minor details. They are some of the central defining features of mammal biology, and the record of synapsids shows that they were assembled deep in Permian and Triassic time, not invented fresh in the Cenozoic. That is why before dinosaurs matters so much here. The Permian was not an empty waiting room for later stars. It was a world in which synapsids were major terrestrial vertebrates, and in which the branch leading toward mammals was already experimenting with stronger bites, more specialized feeding, and a body increasingly suited to a different way of living on land. The point is not that Permian synapsids were secretly small furry mammals in disguise. They absolutely were not. The point is that they belong to the lineage in which mammalian solutions first began to accumulate. If you want to know where the foundations were laid, you do not start with the rise of primates, or even with Jurassic mammals. You start with synapsids and therapsids in a pre-dinosaur world that looked nothing like ours, but was already shaping some of our most basic biological inheritances. The skull tells this story especially well, which is fortunate because skulls are among the fossil record's favourite ways of being useful and unsettling at the same time. In the mammalian line, the dentary becomes larger, the old post-dentary bones are reduced, chewing becomes more precise, and the ancestral jaw joint is gradually replaced by the dentary-squamosal arrangement familiar in mammals. The old quadrate and articular are eventually repurposed into the incus and malleus of the middle ear. That is such a dramatic rearrangement that it can sound almost fictional when stated plainly, but it is one of the best documented transformations in vertebrate anatomy. The point is not only that mammals hear in a special way, it is that the route to that hearing ran through the jaw of our deep Permian and Triassic ancestors. Part of the human ear is, in a very literal evolutionary sense, a recycled synapsid jaw. The teeth matter just as much, although they do not usually receive quite the same public admiration as giant predators or asteroid impacts. Mammalian heterodonty, the division of the mouth into incisors, canines, and differently functioning cheek teeth, was not invented late. Reviews of cynodont and early mammal anatomy emphasize that differentiated, more complexly occluding teeth were already appearing before true mammals, and that this transformation was central to the mammalian way of processing food. Better oral processing means more efficient feeding, more energy extracted per meal, and eventually more metabolic freedom. It is not glamorous, but it is fundamental. Human teeth, for all the trouble they cause dentists and orthodontists, belong to a feeding system whose deep roots run back into pre-dinosaur synapsid history. The same is true of the body more broadly. The origin of mammalian endothermy is still debated in detail, and recent work suggests it emerged stepwise rather than as one neat event, with different aspects of mammalian physiology appearing at different times. But the broad pattern is clear enough. Through therapsids, cynodonts, and early mammalia forms, the lineage was becoming better at sustained activity, better at coordinating breathing and chewing, and better at carrying a larger share of its environment inside itself. That kind of body did not appear only after the dinosaurs disappeared. It was being assembled much earlier through long practical revisions in posture, respiratory architecture, metabolism, and growth. So when we say humans are a Permian story, we do not mean only that our ancestry passes through the Permian. We mean that some of the key operating principles of the mammalian body were already under construction there. Then comes the part of the story that should make anyone a little less casual about their own existence. Around 252 million years ago, the Permian mass extinction became the largest biocrisis of the Phanerozoic, with roughly 90% of marine invertebrate taxa disappearing in a geologically short interval and severe losses on land as well. Nature communication studies place the event at about 252 million years ago, estimate extinction duration on the order of roughly 60,000 years, and link the crisis strongly to environmental disruption associated with the Siberian Trap's large igneous province. This was not merely bad luck for a few ecosystems. It was an event capable of nearly erasing the branch from which mammals would eventually emerge. If you like your evolutionary stories tidy, this is the point where tidiness should give up and go sit quietly in another room. Before the extinction, therapsids were diverse and important. After it, that diversity was cut back brutally. A few synapsid branches survived, including lineages of dicynodonts, therocephalians, and cynodonts, but the broad Permian world of synapsid dominance was gone. The future of mammals passed through a bottleneck so narrow that from our perspective it is almost absurd that it worked at all. The line leading toward mammals was not guaranteed a place in history because it had evolved interesting teeth or a promising jaw. It continued because enough of it survived the worst mass extinction Earth had seen. Human beings, for all our love of planning, owe an unreasonable amount to a lineage that simply managed not to be finished then. And what survived did not stride into the next era as the obvious heirs of the Earth. Quite the opposite. Through the Mesozoic, as dinosaurs rose and diversified, mammals and close mammalia form relatives remained mostly small. Yet small should not be mistaken for unimportant or simple. Fossil evidence now shows that mammals in the dinosaur era were not just generic little insect eaters. Research on Mesozoic mammals and mammalia forms shows a range of diets and locomotor modes, including climbing, burrowing, swimming and gliding, and studies of morphological evolution point to a major adaptive radiation by the Middle Jurassic. So the descendants of that Permian branch were not asleep under a log, waiting for a future opening. They were diversifying actively for a very long time beneath a world dominated by dinosaurs. That long dinosaur era apprenticeship matters to the human story too, but in a secondary way. It did not create the mammalian toolkit from scratch. It tested and refined it. A lineage that had already acquired a better jaw, more specialized teeth, an increasingly sophisticated ear, and a more internally managed body now spent well over 100 million years surviving at small scales. Many researchers consider early mammals to have passed through a long, nocturnal bottleneck, with life in darkness shaping their senses, behavior, and ecology. The idea is not that every early mammal was a perfect little night specialist. It is that living under dinosaur-dominated daytime regimes likely favoured small, often nocturnal mammals with acute hearing, smell and flexible feeding. The mammalian quietness that later primates inherited was honed there, but the deeper anatomical toolkit was older, so when the non-avian dinosaurs disappeared at the end of the Cretaceous, mammals did not suddenly become interesting. They became unconfined. That is a very different thing. The Cenozoic expansion of mammals was real and spectacular. but it was an expansion from a long-prepared base, not a fresh invention. The traits that made mammals capable of radiating into herbivores, carnivores, swimmers, flyers, diggers, and eventually primates had roots reaching far behind the dinosaur extinction. The Permian established the branch. Therapsids and synodonts built the key parts. The end Permian crisis nearly destroyed them. The Mesozoic preserved the surviving line in reduced but diversifying form. Only then did the post-dinosaur expansion unfold. If you remove the Permian foundation from that sequence, the later story stops making sense. That is really the heart of the claim that humans are a Permian story. It does not mean Homo sapiens were somehow lurking in the Permian in any disguised or mystical form, which would be both wrong and deeply unsettling. It means the branch of life that eventually led to humans acquired its defining direction there. The fundamental divergence from the reptile and dinosaur line was already ancient by the time dinosaurs appeared. The main mammalian architectural breakthroughs were already underway before dinosaurs dominated. The great extinction that nearly removed the lineage happened before the dinosaur era. And the mammals that later survived beneath dinosaurs were descendants of a much older synapsid experiment, not a new enterprise that began after the giants were gone. There is also, I think, something useful in how this changes the scale of our self-importance. Humans like to imagine ourselves at the dramatic end of history, and to be fair, we have invested heavily in behaving as though that were true. But the deeper story is less flattering and more interesting. We are not the culmination of a march that started with mammals after the dinosaurs. We are the late arriving descendants of a branch that endured an ancient split, spent the Permian reinventing the skull and body, barely survived the greatest extinction of all, then persisted in small forms through the age of dinosaurs before eventually diversifying into the mammalian world we know. That is a much longer, stranger and more contingent inheritance than the usual version allows, and it changes how you look at quite ordinary things. The way your teeth meet when you chew, the tiny ear bones carrying sound inward, the fact that you can breathe steadily while using your mouth, the fact that your body produces its own heat and can remain active in cool darkness, the fact that mammals are still the only surviving synapsids at all of that belongs to a lineage whose identity was forged before the first dinosaur ever stepped into view. None of those traits evolved for humans. None of them were waiting for us. They were built because they worked for synapsids and therapsids in worlds so old that the continents themselves were arranged differently. We inherited them much later, but we did not originate them. So perhaps the simplest way to say it is this: humans are a mammal story, and mammals are a synapsid story, and synapsids are, in a very deep and literal sense, a Permian story. The age of dinosaurs shaped the survival and refinement of mammals, yes. The Cenozoic shaped their expansion, certainly. Primates and apes shaped the narrower path to us. But the deeper foundations were laid much earlier, in that older world of therapsids, synodonts, changing jaws, differentiated teeth, and bodies learning to live with more energy and more internal control. Before dinosaurs, something really was becoming us. Not in outline, not in appearance, not in destiny, but in structure. And after all that distance, all that extinction, all that survival, that may be the strangest and most humbling part of the whole story.